I'm alive, I hope. Hello, everyone. Good evening. Hope you're all doing fine. Yeah, little last minute decision to do a stream about this. One of the things that sort of came in between, this has been discussed within the rendering team for, well over a year, I think. Oh, my sound says that I'm overpowering it, so let me turn that down a little. Let me know if my voice is too loud or not loud enough, and whether it's coming through correctly. Hope it's good. Anyway, as I was saying, so tonight we're going to be talking about custom shader templates, and it's been a feature that that we've been talking about for quite some time, as something that we wanted to implement. I kind of was between things and decided to give it a crack and see if I could get it to work. So there is currently a PR. Here we go, 94427 that that implements this feature for both the Forward Plus renderer and the mobile renderer, and has all the basic functionality in it. So we're going to do the compatibility renderer soon after, once this is merged. This will, by the way, not be merged until after Godot 4.3 is released. And even then, of course, if it gets approved, you know, there's no certainty there. People need to review it. People need to give feedback on it. And then if everybody's happy with the way that it works, then hopefully we can get it merged for 4.4. So after this initial version is merged, then I will add support for the compatibility renderer. And then we have a number of things that we want to do afterwards to make it usable for other parts of the system and to make it easier to use. So that's important to keep in mind with this functionality. So what is it? That's probably the first question. And quite simply put, when you look at a shader, and this middle cube has got a normal shader, it's easier to talk about shaders through that one. So when we look at a shader, this is what in Godot people will write as a shader. A very tiny little bit of logic. There's a vertex shader here, which allows you to do some calculations that are executed for every vertex on your mesh. And then you have a fragment shader, which determines, which is run basically for every pixel that we draw, and determines the color. Now there is a little bit more going on here because in the fragment shader in Godot, you specify the base colors. After that, all the lighting calculations take place. And then inside of the lighting calculations, you can actually create a lighting function as well to control the lighting a little bit. But what is important to realize is that this is 1% of the actual shader logic that is being run. So this code is actually injected into what we call a shader template. And Godot has always had, for 3D rendering, a shader template that's built in. It has one for all the 2D rendering. It has one for the sky rendering. It has one for particles, etc., etc., etc. Anywhere that we have a shader that we can specify, that we can build here, that code is injected into that built-in template. And quite simply put, just to scare everybody a little bit, when we look at the source code in Godot, in this case we're looking at the forward cluster renderer, so the forward plus renderer. Yeah, that is the shader that we're talking about. That's still going, and it's still going, and it's still going, and still going, and going, and going, and going, and we still haven't reached the end yet. Yeah, we're still going. Yeah, there's the end. Over 2,000 lines of code, of shader code, and we actually have a few include files here. We have a bunch of include files here, like this one, this one, this one, that are actually included into this. So the actual shader code for rendering a cube is, yeah, probably towards 3,000 lines of GLSL code. So you can see that, yeah, this is tiny bit that you have control over. And the nice thing about that is that as a result, all the complexity for making a shader do all the cool things that we're doing, from, you know, all the PBR stuff, so reflections and sky contribution, and you know, obviously all the different material calculations for making a material look reflective or rough or anything like that. All that logic is all nicely implemented in a big template shader, and you as a developer can focus on just the nitty-gritty bits of how you want something to look, instead of having to deal with that you know, or actually have to write that whole shader code yourself. However, that isn't always what everybody wants to do. An example of that's come up in the past that this would actually allow you to do. So the custom shader templates, as the name kind of suggests, is that we allow a alternative to be used. So instead of using this really big shader here, this big template here, you can create your own. And that has a lot of use cases. The most common that I've heard that people want to do is they actually want to use this as is, but they want to add a little bit. Now, that's going to be a little bit more tricky in the first iteration of this, because that would, you know, basically require you to copy all these, you know, 2,000 plus lines of code and then add your little bit at the end or wherever it's needed, with, you know, a big risk that the next version of Godot that comes out that has changes in the built-in template, then obviously your version is now outdated, and yeah, you have a problem there. One of the plans that we have, and this is going to be a follow-up to the initial PR that we've built right now, is to start moving a lot of this code into include files, so that you can actually include all the bits and pieces of the built-in template into your own template, and just add the bits that you want yourself. And again, a good example of that that's come up is, for instance, a toon shader. Right now, you need to do some funky things with a toon shader, and a number of things are done in post. But you can actually add the required code here at the end of the shader, and, you know, save yourself some performance that way. Another use case for this, which is the use case that I'm personally interested in, is replacing the entire template shader with a simpler shader, because obviously it is nice that we have, especially in the Forward Plus, we have a shader that does all sorts of funky things around, you know, PBR materials and all that sort of stuff, and supports, you know, to the nth degree lights and God knows what. But that costs performance. That's why the Forward Plus renderer is targeted to be a desktop renderer for AA towards AAA games. If you want something that is simpler, you're stuck with the built-in stuff. So for me, as a VR developer, and especially targeting, you know, standalone devices, I might go for the mobile renderer and already save myself some performance. But I might even want to go a step further and create my own custom template that removes a lot of the lighting complexity and goes back to much simpler lighting, therefore removing a lot of the overhead that's in these shaders and sort of slim them down. And while they can do a lot less, they might be more performant, or they might be doing something specific to my use case. That is the goal of this functionality. So when we're looking at this very first version, like I said, we are not going to make it possible yet to include all the bits and pieces of the internal shader, the internal built-in templates. That's a follow-up, but we have made it so that we've got some of the core bits that you require to sort of create your skeletons, you create your setup, to import those into the into your own custom template, and start with, you know, a much simpler base. And that's also something that we're going to do during the stream today. We're going to start with that base, and on top of the base, we're going to implement a very simple, what we call an LdotN implementation. LdotN simply standing for, you know, L being the vector for where the light comes from, N being a normal of your surface, dot product of the two, that gives your lighting. Hey Benjay, how you going? So that is the you know, one of the simplest and oldest way to do lighting calculations, but it's not realistic. It's you know, it doesn't do anything very special, but it's cheap. And that is what I wanted to accomplish here. Now, for my sort of use case, I would probably then go and say, I'm only going to support one light so that I don't have loops in my logic. That would be something that I would do in the forward mobile renderer. But since we're now starting off with the forward cluster, I'm actually going to look at how the clustering works and how you can embed that into your template. And we will process that logic for each and every light. So let's see how far we get with that tonight. I'm not sure how far we go there, but we'll build it up and see how far we get and see what we can get working. Obviously, my little test scene here with 3 cubes is way too simple for what we're planning to do to really make it shine. So maybe we'll add some assets in later on and see what we can do with that and what we get. All right. So what else should I cover just as the introduction? So talked about what the PR is. Oh yeah, that's I will definitely, once the stream is over, put all the links to these things in there in the description. I don't think they're in there yet, so I need to just copy paste them. But like I said, this is the PR that we're looking at. And again, I can't stress enough, it's not merged into master. It will not be in 4.3. It will be, if it is accepted, a 4.4 feature. I also have a repository here, which is the repository that we're currently working on. So our little cubes with just a forward clustered implementation in there. I am working. Oh, I haven't pushed that up yet, so that's only local. I am working also on an example using the forward mobile renderer. Like I said at the beginning, we support both forward plus and the mobile renderer at this point in time. Compatibility we will add in due time as well. The other thing that is really important is that obviously when hey Cyber, how you going? Shaders, water, rain. Yeah, who knows? You might get quite somewhere with that as well at some point. What was I saying? Oh yeah. So the other thing that I find very important to mention is that we currently don't have a system to control what the built-in variables are. So, for instance, when you go here, we have like access to our view matrix, your model matrix, your inverse view, etc., etc., etc. Now, some of these will work, some of these won't, and that is completely dependent on what you actually implement in your custom shader. If you don't implement something in your custom shader, then obviously it's not going to work, even though the built-in template does have support for it. Now, because of the way that we include certain things, as we'll see in a minute, we're going to bring in a whole bunch of things that are standard, and as a result, a whole bunch of things that will work as standard in this. But there's a whole bunch of things that obviously won't. Now, and a good example here is that right now the template that I have, which is a very bare bones template that doesn't even have lighting. So obviously these cubes, both of these use my my template code at the moment. They even though my so if I, for instance, look at cube 1, which is actually a material, well, I've set per pixel shading here, and diffuse mode is burly, and I can do something with my metal here. Then nothing works. Why? Because I haven't implemented support for that in my template. And while for a lot of things we can quite easily prevent at least compile errors happening when you use something that's not supported, there are things that if you don't put them in your template, then obviously if someone tries to use that, then there will be a compile error on the shader because it's missing logic. So that is very important to know when it comes to building these templates, and especially when you're building templates where you on purpose are limited the functionality because you want to get more performance or something like that. Then obviously you need to be careful that even though we support it on the material, your template might not support it, and you might get into trouble there. An interior mapping shader template. I'm not quite sure what you mean by that, Catherine. I think we're talking about something quite different here because we're talking about building the built-in shaders here. So elaborate a little bit about what it is that you are interested in with interior mapping. Well, I get another bit of drink. Huh. Okay, where was I? So yeah, so it's going to be important that depending on how broadly you implement your shader functionality, that's especially in materials. If you don't support functionality in your template, then things will break. It's that's unfortunately part of the deal. That's also one of the reasons why I personally like to use it with a normal shader like here, because you limit it to actually stuff that you want to use. Now, one thing that we haven't got in here that that maybe will come in the future, but I don't think that will be very early on, is to add your own build-ins. So right now you are the only things that you can use in here are the things that Godot exposes normally, and your template can either use those things or ignore them. You can't add new things. So if you have some sort of new variable in your template that you want a user to set in their user shader, you can't. That's currently not part of the plan and part of the capabilities of this. Might come at some point, but not right now. So yeah, that's something that we're still thinking about and sort of contemplating. Okay, how can we improve on that and make that work? It's just too much in the core of what we're doing. Dev, yeah, that is actually well, yes and no. In theory, you can get a long way with this, I think, if you want to do something like ray tracing, or at least where you're still doing normal polygon-based drawing, but then, for instance, you want to ray trace your reflections, because you do have access, especially in the Forward Plus renderer, you do have access to a lot of information. But when you look at a full ray tracing implementation where you're really using the abilities of the the special ray tracing functions of the GPU, you would need to do a lot more. You would actually have to also implement a whole bunch of things in the renderer itself. It wouldn't be enough just to do the shaders. But there is a lot that you can indeed do, and especially with the way that we've approached this, that you can set this on a material or even on a shader level, and you can mix it with normal. It's not like you create one and that's what you use everywhere. Even in this example, the ground and this right cube are still using the built-in templates. These two are using my my hardly anything capable custom template. So yeah, that is there are then possibilities that you can get pretty far with how far you can customize, and you could then say with the limited number of objects you might want to do some more advanced ray tracing sort of techniques. You probably can get pretty far, but again, to do a full ray tracing renderer, there is more that you would need to do. You get far, but not, you wouldn't reach the end line with that one, or the finish line. So write a template that stops the renderer from automatically putting an object with a shader that writes the depth buffer in the transparent queue. This one, how is to write a template that stops the renderer from automatically. that's controlled separately. That's controlled by your render modes, whether you are writing into the def buffer or not. And as far as I'm aware, could be wrong, but as far as I'm aware, during the transparent queue, we by default don't write into the def buffer. Because that's all handled by the different pipelines that are created and not specifically code in the shader itself. So not quite sure about that one, Jay. I would say that is something that you would control with the render mode. So where are we with those? Let's forget where they are. So yeah, we have our def draw, whether we only draw in def in opaque, or that we always draw def, or that we never draw def. So that's where you control that, and those are just render modes. So if you, like I said, by default we only write into the def buffer in opaque mode. And obviously, if you want to ignore def altogether, you can disable the def test. So again, that's also a render mode. So yeah, you specify that in your render modes over here, and that just controls which part of the pipeline is enabled, and it doesn't actually change the shader code. The shader code is pretty much ignorant of what you're writing, or that's just base logic in the pipeline that you get for free. So I hope that answers your question there. So where are we? So the templates are stored in these GD template files. Now, unfortunately, I don't yet have an editor in Godot itself. So right now, just like with GLSL files, you need to edit them in a code editor. And of course, I have that off screen. That's not good. So here we can see my my test template, which is already a good 350 lines long, even though it has just got some basic stuff in there. So we'll go over that one in a second to sort of go over what is pretty much the bare minimum that needs to be in here. And again, eventually we'll start cleaning that and tightening that up even a bit more by allowing you to include other parts of the built-in shader, so that you don't always have to remember what bits need to be in there. So yeah, no, that's right, Catherine. That's a problem with a name as template being so ambiguous. And there is a discussion going on right now whether we want to keep the name the way that it is right now, or whether it's a too confusing name. We're not sure yet. In that way, anybody who has suggestions for a better name, we're definitely willing to hear for that. But yeah, template is a very ambiguous name. So yeah. There will be some confusion, probably whatever name we choose. But for now, we chose that name. It's been a name that's been kicking around for several months when this idea was first raised of implementing this. But yeah, we'll have to see whether we stick to that name or whether we name it to something that fits better, depending on what the suggestions are. Justin, yes, I am not a fan of dark mode. So I'm one of those few people who actually uses bright mode or the normal light mode. This is actually one of the standard color themes in VS Code. So yeah, call me old-fashioned. I don't know. It's just something that stuck with me. Anyway, so there's two options right now. One, obviously, which we have on Cube 2, is just that we have a normal, a normal shader material over here with a shader put onto that. So there's our GD shader, and in that case, you can simply specify the shader template that you want to use at the top here as a new bit of code here in in the shader. If I disable this, it goes back to using the built-in template. So now it just functions just normal. But yeah, if I put that in there, then it says use that template, and it will use that to inject our code into. There is no limitation to the number of templates that you can create. So if you want to create a template that does something very special with, I don't know, for a special sort of water shader where you want to do something really cool that you can't just do here, that you need to do more code with, and you have another one which is for your normal materials or whatever, you can create multiple templates if you want. It'll be a lot of work, but you could. So yeah, that's the way to do it with just manual shaders. If you look at a material, you can just simply find it under the shading settings. There's the shader template option, and you can just drag the shader template in, or you can go to load. You can select new shader template, but it doesn't really give you any access. It's kind of the same as other places because we don't have an editor yet. I still need to look at whether I can easily add a shader editor in there. Marcellus, I'm gonna have to write a bunch of custom shaders based on matte caps of reflection probes to get the look I want on Quest. Yes, and at the same time, no, because reflection probes on quests, you want to use those to reflect your environment, or you actually want to calculate reflection probes around a VR scene? Because that could be pretty costly for a device like a Quest. But yeah, you could probably do quite a lot of things with this to at least optimize that a lot. That's for sure. Kiwi, how you going? I've hardly started showing off things. So the compositor effects definitely were very well received, and I'm very happy to see lots of people making incredibly cool stuff with that. So yeah, I'm very happy that is a feature that people really enjoy using. Let's see if this is also something that people will take on board. This is definitely a lot more complex to do something with than compositor effects, and I think that this logic will stay experimental for quite some time before we can really get it nailed down. But at the same time, I think this is a really solid base for what it is that we're doing. So let's see how people take it on board. All right, so the last thing that I want to talk about before we actually start having a look at our shader is that seeing this is brand new and seeing that it's going to take a long time before people really get some experience with this, and information will be out there in how you customize these templates or write these templates. Sorry, just seeing QB come in. Yeah, I did give an introduction into what this is about. So when we're looking at our built-in shader, our nearly 2250 something lines long shader in here, into which our user shader code is injected, which then builds the actual shader, that the custom templates are designed to allow you to create your own version of that, either by duplicating the built-in one, which I think for version 1 is not something that people should do. There's still a number of things that we are going to be doing to make that easier, plus that there's a bunch of rewrites probably coming around that logic, because there's a whole bunch of performance optimizations coming in, like the work from the Forge that is slowly being merged, although that mostly impacts the mobile renderer. But there's other things that that will change how the shaders work. So yeah, as not until we move more logic into include files that you can actually include, so that you can actually piggyback on those changes. Copying the whole shader is a bit of a what you call it, is a bit of a no-go right now, but you know, starting something from scratch is definitely something that you can do. Yeah, so one of the specify extra functions, like make a new entry point here, so that you could do my function and then have that injected into the template. That's a really neat idea. No, that is not possible right now. And kind of also something that I mentioned, that, you know, like all the built-in values, like, you know, UV and albedo, you're stuck with the ones that we currently have because of the way that the shader compiler works. So you can ignore them if you don't want to use them, but you can't add to them right now, not in this first version. So the first version is really meant. Well, the post light is something where, again, that was one of the examples that I mentioned. So you couldn't add the logic here, but obviously you can add the logic at the end of your shader, or, you know, you can fake it while you make it. Like if you don't need a you know, if you don't need what is it called, light, I think. You know, if you don't need the light function, you can change your template and say, I'm actually going to abuse this as, you know, this is secretly my post light function. You know, that's something that you do have control over. You just can't create new functions yet that you can inject. But that is a really nice idea. I wonder how we could add that in. So definitely put that as a request on the PR. And while I won't be able to add it into this first one, that is definitely a nice enhancement to do, that we can define our own functions and insert those. So again, I do want to stress that right now, today, if you would be using this today or base something on this today, you don't want to, because this is the idea that we have, right? What we eventually want to be able to do is that you go into the source code, maybe we publish this somewhere even, and you just copy paste the built-in shader and you add your own stuff. Now, if you do that today, first of all, it will error out because some of the includes aren't exposed yet, but also there is a high likelihood that this code will change over the next couple of versions. So if you built your template by copy paste of this, you'd likely end up with something that becomes, you know, outdated in a couple of versions and might even break, and you'd have to do your things again. So there's going to be follow-up work where we're going to start moving many of the functionality that's in here into includes, that you can then include into your template, and then you can just call the built-in logic and add your own logic to it. That's future music, but that is definitely in the planning. Where we are today is that you can build completely your own within the skeleton that we've created, and within limits that will likely survive future versions. There might be small changes that you need to do, as we, for instance, Dario is currently working on introducing our Uber shader system. So in order to make use of the Uber shader, there's a couple of small changes that might impact any template that you create today based on the information that I'm showing in this stream. But again, you know, this is not even merged yet, so this is very early on. The same situation that we had with when I did the stream about the compositor effect. It wasn't even called compositor effects back then. It was called rendering effects. That changed over time. That got improved over time. But all the core stuff will probably be there. Bartidev, right now, the only way that you can do that is by creating a second instance of the bowl. There is currently no functionality in Godot where you can vary the shader used depending on what viewport you are rendering your object in, which I really wish we had that. but that's not something that we have right now. The only thing that you can do right now is, where are you? On layers. So if you look on any mesh instance, and this is also on other objects, so like particles and on multi-meshes and everything like that, you have this visual layer system where you can specify which layer that object is on. And when you then create a camera, oh, here's my camera, then you can define which layers you render. So you could have one camera that only renders layer 1, and then on your other viewport you have a camera that only renders layer 2. So that is the only way that you can currently create a situation where two viewports render things slightly differently. I really wish that we had a mechanism, because there's a couple of situations where I want that as well, where I want something to render differently in different viewports. Unless QB, you might have suggestions there. I don't know if there's another feature that I'm not aware of that might be able to do that. But as far as I'm aware, right now, we do not have a feature that allows us to do that. So, and you know, the shader template, would that have something to do with it? No, I don't think you could wrap that in there somehow either. Yeah, no, not. I wish we did. I really wish we had something where you could say, you know, use this material layer on layer 0 or layer 1, use this material on layer 2, and then have the camera say like, hey, the camera's on layer 1, and therefore I'm going to render all layer 1 materials or something like that. That would be really cool, but right now I don't think I don't even think that's on the roadmap or on anybody's radar. Yeah, I do agree. It would be really nice to have that feature. It's something that I've missed from time to time as well. Because especially like when we're looking at stuff like VR, where you would often use an extra viewport for some effects or something like that, you'd often want to render something with a different material. So yeah, you would really want to be able to switch different materials per viewport, and that's probably also the most efficient way to make that happen. Well, no, the deferred renderer, you're probably going to actually limit yourself a whole lot with these sort of things, because yes, you're writing all these intermediate values like your albedo color and your your roughness and everything like that into separate buffers, but then the compositing is actually a single stage. So basically, this guy will not work on a deferred renderer. So that's a big no-no. Basically, your output of your fragment shader, that's what's going to be written into all the different buffers, and then you have a single light pass that will, have a fixed light implementation that runs and shades everything. That's unfortunately one of the limitations of a deferred renderer. All right, I get what you mean, Bartodef. Yeah, that's. I wonder how they do that with Material Maker, because he works with that as well. Yeah, QB, I agree. That I don't think anybody has the different materials per viewport thing on their radar at the moment. Yeah, I really wonder what would be a good way to do it, because one of the things that I do miss, and that I think we oh, those are alt arrows, I hope. One thing that I really do miss, and that that I think would be something that we could add, which is potentially not super hard, is I miss a way to know which camera we are rendering with. So it would be really nice if we have some sort of unique ID on a camera ID, and there's obviously a node ID or a resource ID in the background, that is actually exposed as a variable to the shader, so that you could at least in a custom shader do something. If camera 1, do this. If camera 2, do something else. And then that would be an interesting way to solve certain things as well. But that is kind of other use cases again as well. So not quite sure about that. Okay. Or, one of the things that might even be cooler is seeing we have, things like environment, attributes, compositor on the camera. Is that we could have additional, just like we have local uniforms and global uniforms. So we could have camera uniforms that we could then implement on the camera. That would be interesting. I wonder how we could make something like that work. Food for thought. Anyway, yeah, the per layer material would be really good, but that's really something where, which I think is a fairly big change on the system, because again we have already so many layers, right? We have the material on a mesh. Well, this is even with obviously a primitive mesh where we just have one material, but if it's an asset that you load in, you have a material per surface. Then obviously for every surface we have an override, then we have a geometry override. So how, especially if you have got 5 surfaces, do you then want to have a big matrix of surface by material layer or something like that? I'm not quite sure how you would make that work in practice, or is it then something that we only do on the material override level or something like that? I really don't know. That's an interesting discussion. I like the discussion itself, but yeah, it's a bit of a distraction to what we're dealing with today. But yeah, food for thought. It would definitely be interesting to figure out what would be a good way to change materials based on layer, or to set materials based on layer. Okay, so let's go have a look at the template that we currently have. So like I said, that's our little test template that we have currently, and that we'll start having some fun with today. Now, oh yeah, that was actually the thing that I was going to mention when we got distracted. So right now there is very little documentation about this, and it will take time before documentation becomes, to a point where you can really understand how you can build certain things. And even then, the problem that you will always run into, this is core. This is hardcore even. If you do not understand enough about how the internals of the render engine in Godot works, it will be near impossible to write something from scratch. Especially if you try and look at, some special code that someone might have written on another rendering engine, and you say, hey, that would be really nice to have as a template in Godot, so that I can use that in Godot as well. If you don't know enough about how Godot works internally, you'll likely get stuck. I think we'll eventually make that a lot more friendly by exposing more and more things in nice chunks and rewriting things so that they're easier to use or reuse in templates. But I still think that even when everything's done and dusted, templates is not, or custom shader templates are not for the faint-hearted. You really do need to have a good understanding of how the render engine works. And with the limitation of the documentation, unfortunately, there is no better thing than actually knowing where everything is in the source code of Godot. And for this stream tonight, even though I've made everything work both on mobile and Forward Plus, we are going to stick to the Forward Plus renderer. So if you're in this location here, and this is obviously on a folder on my server. Actually, I might actually go and show that slightly differently by simply going to the main repo. If you go into servers and you go into rendering, and then the RD renderer, then you'll find this is the normal implementation. So you have to go one more layer deep, shaders. Now here you find a lot of standard shaders. Some of these are applicable, but for what we're doing right now, we're going to skip over most of those. There's one that we're going to be looking at eventually. But in the folder forward clustered, here you will find those. Now, obviously, this is master. This doesn't have our changes in there yet. So here you can see that there's only our scene forward clustered and then a scene forward clustered include file. While, I got too many windows open. While in this, I have 1, 2, 3, 4, 5 files. So after this is merged, we'll have 5 files because I've already started grouping things together a little bit better. But even, you know, and we'll be referring to this, in order to actually write your own templates, you're going to have to start getting comfortable with at least looking at some of this code to get some of the quote-unquote documentation that you need. Custom viewport debug files. I don't know. The debug thing is that's a complete overrule of things. That's pretty much a yeah, that's pretty much a the wrong path to go down, I think. Yeah, it would be nice if we could find the solution for that, QB, but I'll actually, last little distraction then. See if I can find it. I think it's called Material Maker. I think it's this one, isn't it? That's made in Godot. Yeah, Godzilla's project. So yeah, Material Maker is you know, procedural material maker, you know, written in the Godot engine. I'm not going to play the little thing here, but it's not Substance, but it has a couple of things in common. And it was trying to think of whether there was another application related to this, or because I thought that he also had a painting mode on this. Maybe I am mixing up with this because that's where Rod started with it, if I remember correctly. It was actually texture painting on an object. Can you remind me, was there another project that Rod made for the texture painting specifically, or was it all combined in Material Maker? So both creating your procedural materials and then actually painting with it. Anyway, I can't remember for certain, but Bartodev, if you're not aware of Rodzilla's work, definitely go and check this out. It's and he does a lot of that stuff as well, where he splits out everything to different textures so that you can export those and you can actually generate complete PBR materials with this. So yeah. Also, it only has the one preview that it switches. Okay. Anyway, that was one of the things that I thought of that is in that same vein. And I don't have enough experience with it. I've played around a little bit with Material Maker, but I haven't done enough with it to really know what he does and doesn't do. But there might be some ideas there that are in the same direction as what it is that you're doing. Okay, so let's stray away from our 2000 line built-in one and start having a look at our little test template. So this is the bare bones template that we've got in our project. I'm probably going to duplicate this and then do something more specific in a new template, because I want to leave that one alone. Although I'm not quite sure if I'm going to check in tonight's work or whether I'm going to park that for later or anything like that. But basically, I wrote this as an example of the bare minimum that you need in order to get a template to work. Unfortunately, I can't fold or unfold things in here. That's a bit of a shame. We do start with our shader type at the top, and I'm not quite sure if I actually do something with that yet at this point in time, because only spatial shaders support this at this point in time. But if we also are going to offer custom shader templates for sky shaders and for God knows what other shaders that we have, then I wanted to have that at the top, so that Godot can at least check whether you're using the correct one and you're not accidentally using a sky template with a spatial shader, or a canvas template with a fog shader, or God knows what sort of weird combination you could make. So that's purely why that's there. The next little bit here is this keyword vertex. So this is our start of our vertex shader. Now, one thing that isn't in here yet, but that came up today, or I think even yesterday, but QB, you mentioned it also to me today. So one of the things that I'm thinking about is adding another grouping here and saying, this is forward clustered, and that it therefore knows that now the forward clustered version starts. And then at the end, you could have forward mobile, and then have the mobile version, and then compatibility, and then have the compatibility version, so that we can switch between different sets of shaders or templates depending on what renderer we're using. Right now, that's not the case. So this is a template for the forward clustered shader. If I use this on the mobile renderer, then I'm bound to get errors, because there are slight differences between those. Because of that reason as well, if I go back to, where is it? I go back to my, that's right, I hadn't uploaded it yet. I will upload that either tomorrow or over the weekend. There will be a branch here that has the mobile template. All right, Bartadev, nice of you to join, and till next time. And good luck with your issue. I hope you find an answer for it. So yeah, I have got a template for the mobile renderer that I will be adding in here, but there's still a couple of questions that need to be answered before I merge it into master. But I will be putting the PR up on that repo. Okay, so we have a keyword at the top to say that the text that follows is our vertex shader for this template. This is just standard DLSL to indicate that we're using or that we're writing a shader compatible with OpenXR 4.5 or newer. Sorry, something's. Yeah, so that's just something that we put at the top, and I'm not sure if it's OpenGL or GLSL version. I'm not quite sure what the numbering relates to. I always forget that one. But it basically defines or tells the shader compiler what version of the shader language we are using, and therefore it knows how to translate certain things that it finds properly to to the actual machine code that we're using in the background, or GPU code in this case. Then we have this little thing, version defined. So a lot of the times when we see these preprocessor functions with a hash in front, they're either like defines or includes, but we also see a couple of these. So we also have here hash globals, for instance, and these are placeholders that will be replaced by code that is generated by Godot itself. So in this case, Godot doesn't just compile one version of your shader. Godot actually compiles multiple versions of the shader, and it will insert defines at this place that tell you what features are relevant. Those features can be, are we compiling it for when we're doing, when we're running our shader for shadow map creation, or are we doing it for rendering out color, or are we are we running it in stereoscopic, etc., because your code will react to that. But you also have, for instance, defines such as here that are triggered by your user code. So right now, I'm only using albedo and UV in here. So for this shader, normal used will not be defined. So this bit of code will not be included. UV used will be defined because I am using UV here. So there's all sorts of things that get filtered out or added into your shader depending on, you know, what mode we're in, what variant we're building, what things are used in the user shader, and that allows us to further optimize the shader for a particular use case, which is really cool because else you would have to write, you know, hundreds and hundreds and hundreds of different versions of one shader just to account for all these different scenarios. Here we just get that things are switched. So which defines are actually used, that is inserted in here. And I remember, and I tried to find it the other day, but there is a way, and I'm just having a look where that is. Because I always forget where Rados has hidden this feature. I know it's in there, I know it exists, but I always forget where it is. Okay, let me just try and do just a gamble here. So I'm gonna say here, this is my test material. So now I have a test material here, and if I open that one, do I now get it? No, so that wasn't it either. There's supposed to be an option that allows me to see the full source code that it generates. Why can't I find it? I can never find it. I know it exists, but is it in here? No. I know that we have that somewhere. I don't know if someone in chat has seen it, but there is an option somewhere hidden in the interface that I can see the full code of a shader. God, where would that be? No. Distress squeaks. Well, if I can't find it, I can't find it. But it would be nice to be able to show it. Yeah, I thought it was somewhere in the inspector. Oh, maybe it's this one. No, hold on. What if I do it like this? That's material. No. Yeah, no, it's in there. I've seen it. I know it exists. I just don't know where it is. Yeah, for visual shaders there is. Yeah, that's what would be logical, right? That it's over here, like, you know, show total shader. But God, where? Maybe if I do this. No. No. I just know it exists. Rados showed it to me. You had it. Inspect native. Where did you see it? Ah, did I really just have it and not see it? Okay. So we're looking for native shader code. Okay, so it wasn't there. Was it? Oops, that was too far. Shader, was it here? No. No. You had it. Where did I have it? Where did I see it? Oh, this is horrible. Why can I not see it? Go back to material. Okay, back to the material, because I think it was indeed on material. That's a doc. That's not what I wanted. Here, copy, paste. Inspect native shader code. There we go. Okay, why is it not opening? Because it's still running. It's doing something. Yes, it's stuck. Okay, come on, don't crash on me. Ooh, that's a big window. But that is what it... Oh yeah, because it builds every single version. Because like I mentioned, we have all these versions, right? So here we can see that it expands the whole thing out. So we can see the define. So this... well, actually, the best way to show this is when I go back to... Where are you? So here we have our define. So we can see the first line after that is this line. So that is... where was it? That's that line over there. So here you can see all these defines that are coming in. So there's a couple of defines that are just inserted because of settings. So our max roughness LOD is a project setting that comes in. Here we're saying that we're using our cube map array for whatever reason. We have an SDFDI setting. I don't know which version this is. Mode render depth is an important one. That means that this is a either depth buffer or shadow map shader or variant. And here we can see that our material uniforms are used, our vertex code is used, fragment code is used. Oh, look at that. Those are actually, there's our if that's cool. Our render driver Vulkan is used, which is kind of cool. So that's one version, and like yeah, you can see how many versions are done. So it's a little bit, you know, eeny meeny miny mo, which is the one that we really want to look at. So here we can see a multi-view version. So that's for stereo rendering. That's still stereo. I want to see one of the earlier versions. So I want to find this. So that's still a def. So that's our dual paraboloid version. So that is for omnilight shadows. This is our version if we're splitting out roughness during our depth pre-pass. So that's used for certain effects. Here is one that then also adds the voxel GI. So if you're using voxel GI, that version is used. This is a special material version. So this is the version that is used when you're rendering out, I think, light maps. This one is something that has to do with SDF rendering. And even I don't know every little bit about a rendering engine, so I'm not quite sure what that version is for. All right, then we have our, so now we get our multi-view versions of the same ones. So probably all the way to 10. No, we have less of the multi-view ones. Okay, so I'm going to go one back. I want to go one back. So yeah, this is the last one for our multi-view. So this would be our first normal one. So we can see that our mode render depth is gone. It doesn't have any other things. So this is pretty much the one that we're after. Here we can also see that our UV is used. So what I mentioned that before. So these are the defines that are injected to create all the different variants of our shader. Now some of these are, like I said, project settings, so they will always be the same. Some of these are dependent on your user shader, so the code that you have over there. And then a whole bunch of them have to do, yeah, these are all for that. And then some of them, like over here, you have a whole bunch that are introduced because of the different variants that we create. The normal one, the normal color one, is actually the default, so that has actually the least amount of defines in there. All right. So with that, we now get to this line. So here we're simply defining shaders as RGB as false. That is just a constant that we add in there specifically for the compatibility renderer that actually outputs sRGB. The mobile renderer and the Forward Plus renderer both output in linear color space. And this is used, you know, especially when we include functions or include files that have functions in them. Then you know, they might take a slightly different code path if our output is sRGB. So it might convert from sRGB back to linear, or it will convert from linear to sRGB, depending on what is needed by that shader. So this is something that you likely won't be doing anything with when you're writing a template, because the template is aware of what it needs to do. But for various include files, that is important to make sure that the right code is being executed. Now next you can see that we are including two things, but we're also seeing that there's no path or anything there, and that name doesn't seem to relate to any of those files that we had. And that is because when we look at the renderer, so here I'm going back to the code here, we can see our scene forward clustered standard inc. This is actually the standard include file. And then on the forward mobile, we have a similar file, but now we have our forward mobile standard include file. If our template is processed on the forward plus renderer, we actually include that file. If we do it on our mobile, we include that file. If we will be running on our compatibility renderer, we will be including whatever file we create there. So we're trying to standardize as much as we can to limit the need to know, to make specific changes depending on what renderer you're at. So I'm trying to make everything a little bit more robust instead of, having to change what that is for every different renderer, because every renderer will have a standard include file. And then when we go and look over here and we look at our standard include file, well, the first little bit should be easily recognizable because that is the stuff that we find right over there. So those are a few more extra defines that are specific to the clustered renderer that we just want to define here so that they can be used in the rest of the shader. We can see that we don't support some things when we are doing stuff with Molten VK. Long live the metal renderer coming soon. You can see that we are including a couple of extensions here that are part of GLSL, which allow us to do some subgroup handling. I'm actually surprised that that's in here because that's mostly used in the compute shaders that we use, but we'll probably use them somewhere. I'm not quite sure where, but we include them here because it is something that is available in the Forward Plus renderer, but obviously it is only part of the Forward Plus renderer. So again, you need to be aware of that if you start using those things that you're limiting yourself. There's some code here around stereo, so it's setting up some helpers for stereo rendering. You can see there's a whole bunch of other include files being included that we currently haven't exposed, but cluster data, decode data, and scene data. We will take a look at this one in a minute because that one's actually quite important. Obviously, they're all important, but that one is something that you'll need to be aware of right away. But these basically are include files that, and we can actually see them expanded here. So, for instance, the clustered, we're going to see that there's just a few defines right now. For the next one, which was the decode data, we can see that it brings in this struct. And here's our scene data struct. That's the important one. We'll look at that some more later. So we'll see that there's other places where we start including other things. But this is basically the structures of data that is globally available to us, and that we will be using. Just to quickly go through this because I don't really want to really go through everything that we have here. But there's some extra defines in here just to make sure that we have the right information. Here's our something that's called a push constant. So this is some instance information that we get for every instance call that we get so that we know what we're rendering. And this is where it starts getting really interesting. So another include file. So that one's actually kind of interesting because this is another one that we're going to be using today. This is the structure of our light data. So we have a structure called light data. That's all the information that we have about a single light. And then later on, we'll see that we actually have an input that is actually an array of this light data. And that's just in global memory. And we can access every light that we have in our system through that, which is kind of cool. The same for reflection data. So this is the data that we have on each reflection probe. Here's directional. So this is what we have for every directional light. And then we go to the next little bit. So there's a bunch of flags here that are important. This is our shadow sampler. So the samplers have sort of evolved a little bit over time. So hopefully At one point, we'll clean that up a little bit, but a lot of the default samplers are just available globally, which makes a lot of things much easier. And this is where it gets interesting. So let me just have a bit more to drink. So when we look at data coming into a shader, and then in this specific, global data that's mostly static over the frame, we bind them through uniform sets. So every set, we actually have 4 sets that we have available. And then within every set, we can have a limited number of bindings. And the number of bindings that we have available is defined by the GPU. But we're hopefully still staying on the minimum limits there. But they're basically slots that you can slot pointers into to data that we have previously uploaded by creating uniforms and then putting them together in a set. So I already mentioned the sampler is then on binding 2. Now, and you don't really need to know what these bindings are. Again, this is one of the reasons why we're including that. The only thing that you need to know is that this thing exists. Now, the shadow sampler, you're probably not really going to care much about, but these are the ones that are going to be interesting. So on binding 3, we have a read-only buffer called OmniLights that has light data. Doesn't specify how many, because that is just however big the uniform buffer is that we have assigned to this. But here is basically our array of OmniLights. So this is when we want to do something on the OmniLight. This is how we get to the data for that OmniLight. On binding 4, we have and this is, by the way, the name that we can expose this. So if we want to access this, it becomes OmniLights.data, and then the number, between square brackets, the number of the light. So let's say light number 5 dot color, and we know I'm not sure if it's called color, but we can actually really quickly see that. If we go over here, we can see, well, for instance, position. What's the global position of this light? Oh yeah, I was right. Color. What is the color of the light? Etc. etc. So that's how you get through that information. We have the same for reflection probes. Now in binding 5, we have the same for directional lights. If light mapping is enabled, we have light map data. If light mapping is not enabled, that will just be empty. Some capture data. I don't know exactly the details about the light map system, but that's there. We have a decal atlas, which is kind of nice. And oh yeah, that's actually our decal texture. So when we're rendering decals, we that's the texture that we're accessing to actually get the texture data for that decal. I'm not quite sure why there is a normal sRGB version there, but probably is any, and that should actually be the same texture, just whether there's an automatic sRGB conversion there. Probably has a good reason. Here we have our decal data, so we'll start looking at that for at some point. Here is our global uniform data. So whenever you define global uniforms, so those are uniforms that you set once and the value is the same over all materials using that that variable. Here's where you find that data. So yeah, there's a whole bunch, and I don't really want to go through everything because most of this you wouldn't be re-implementing your own SDFGI implementation, for instance. Again, that's where we want to have as much of that in include files that you can just call and you can just add the SDFGI functionality in. Not available yet. This one's the first set 1, binding 0. This one is incredibly important, which is our scene data block. Now, with the compatibility renderer and the mobile renderer, there's currently only one copy of the scene data. That will likely change. For the Forward Plus, we have 2 copies of the scene data. We have the scene data for this frame, and we have the scene data for the previous frame. So if we go back to this guy, where we can simply scroll up to what the scene data is, you'll see that that contains our projection matrix, our inverse projection matrix, inverse view matrix. It contains copies of those because that's, if it's stereoscopic, that contains our combined frustum, while this will contain our matrices per individual eye. We have a nice little matrix here that's obviously used for billboards. We have a, how big is our viewport? What is the calculated pixel size as a result? We have a bunch of information about our directional light and our normal light for, doing shadow stuff. Yeah, well, this is kind of important, our ambient light information, and there's a whole bunch of things in here that that are mostly based on either settings, either viewport settings or global settings, or based on your camera or anything like that. So, and we have 2 copies of those for our current frame and for our previous frame, provided that that we're doing motion vectors, because only then that second copy is filled with data. So that one's very important. We will be looking at that. And the rest, there's some specific stuff here. Instance data. Oh, this one's very important. So be aware that binding 2, we have a variable called instances. For every mesh instance that we render, will have an entry in our instance data, or actually every mesh instance that currently exists in our scene, whether it's rendered on that viewport or not. That's one big global buffer of instance. Or is that sort of per viewport? Might be per viewport. We might be updating this for every viewport that we render. So don't hold me on that one. But the most important part is it's all in there. So, and again, this is kind of coming back to whoever it was a little while ago who was asking about ray tracing. This is, for instance, where you have 50% of the data that you need in order to do ray tracing. Unfortunately, this does not contain a link to the actual mesh that is being rendered here, because that's something that that is provided, if I'm not mistaken, and bound. Yeah, because we are bounding per draw call here. While in a full ray tracing environment, we would have all that information in these buffers, because we're doing all the processing on the GPU. But that's our core information there. The rest of the bindings, we can see that there's a whole bunch of textures that we're making available. So our radiance cube map, and again, it's depending on whether we're using an array or individual textures. That depends on, cube map is more performant if we have those available, but if that's not supported, then we fall back to, I guess we fall back to a single one. Maybe, I don't know. I haven't looked too much of what's behind here. We have our reflection atlas. We have our shadow atlas, so that's all the shadow maps that we have for all the different lights. We have our directional shadow atlas, so those are our 4 shadows for, and I think this is 4 shadows per directional light that you have, and the more lights you have, the less quality you have, which is something to keep in mind. But hey, you have access to that. If you have light maps enabled, here's your access to your light map textures. We have our voxel GI textures, provided that voxel GI is enabled. That's what's coming in there. This one's going to be very important, our cluster buffer. So this is what makes the Forward Plus renderer so special. The Forward Plus renderer has a step before we start rendering geometry, where we build a buffer with light information, so that for every pixel on screen, we know which lights affect that pixel, so that we can limit in our fragment shader which lights we are processing. And that data is stored in the cluster buffer. So that is something that we will be accessing today. Sampler used for decals, sampler used for light projectors, a whole bunch of extra samplers here. These were all added later. Bunch of things for SDF GI. A bunch of input. So this is depth buffer, color buffer, normal buffer, AO buffer. So these are the ones that are being, and this is the stereo versions or the normal versions. Obviously, depth buffer and color buffer is only available for transparent, for the transparent pass, because they're copies of what's rendered so far. Normal roughness buffer is available if you need it when it's rendered in the depth pre-pass. AO buffer is available if we have an SSAO enabled. Ambient and reflection buffer. Can't remember off the top of my head which effects fill those and make sure that we have data in those. Bottom line is, this is how we bring in a whole bunch of data that is pretty much, for all intents and purposes, global to this rendering this frame. And it's just important that you know that those exist. And again, I'm not going to go through a detailed exposition of everything here, but I just wanted to sort of let you know, like, hey, this is where you find all the data that is input into a shader. So this one is also really cool. Our user material. I don't know if, yeah, look at that. Our comments even stay in here. So this one's actually quite interesting, because when we go to, where are we? Rotation, instances. Yeah, I'm not far enough yet. Here we go. That's all the stuff that we were looking at. So at some point we're going to see, oh, we gotta, oh, how did that get in there? Hold on. There. Oh, yeah, we have a function here. Huh. Okay, a helper function. Also nice to know that we have that. I'm not quite sure what that's used for. We have an helper function there. Yeah, no, I wanted to have a look at the user materials, because here we can see that we're getting a block of data in albedo, UV1 scale, UV offset. Well, lo and behold, if I move this out of the way for a second, look at that. Those are our inputs here. So we have an albedo, a UV1 scale, a UV1 offset. Not quite sure where our texture albedo went and how that's brought in, because we obviously have that somewhere in here as well. But that needs to be a different uniform. So I don't know how that's brought in, but we might eventually run into it. So with that, we have, you know, in a very quick go, we've just had a look at what is brought in standard occludes. So again, that's all our global information that we have available, all our light data, all our, you know, our scene information, all our, you know, shadow mapping information, etc., etc. All that stuff that that basically stays the same for all the objects that we render, with then of course that material bit as the exception. The material bit changes for every material that we render, but basically that is our state that we get. Now, the next one that we include is input attributes. And again, for this, we have done exactly the same thing, that we actually have a scene forward clustered input. And then on a mobile, we have a scene forward mobile input, because those two have similar, but not the same attributes. So what are attributes? Attributes is the information that you get for every vertex in your system. So we can see here that we are bringing in these things, and they are all marked with locations. So in location 0, we're getting something called a vertex angle attribute. And that is because we are encoding some of the vertex information to save space and save bandwidth. Basically, this is the position of our vertex in local space. So in the you know, local area of your mesh itself. So source of your mesh data. And again, we can see that we have, you know, all these defines that we check to make sure that we only include the things that are actually used. So we remove a lot of overhead. Axis tangent attrib, these two work together. This actually contains all the information needed for your normal tangent and binormal, so it's bitangent. But it's encoded. These two together need to be decoded. We'll have a look at that in a minute to get all that access. So within these two inputs, we have our vertex position in local space. We have our normal. We have our tangent and our bitangent. Here we get color. So if you have color attribute information on your mesh, that's where that information is. And what is, by the way, important before I go too far down, is that in your vertex shader, even though this is actually pointing to an array of data for, you know, if you have an object with 100 vertices, that's an array with 100 entries. but in the vertex shader, we're already getting access to the vertices that we're currently processing. So when we access color attribute or when we access UV attribute, we are accessing that information for the vertex that we are currently handling in the vertex shader. That's also why this input is only, this include is only relevant for the vertex shader. Here's our UV2. If we need our UV2, you can see that if it's used in user code, or if we're using a light map, or if we're rendering our material for our light map, we need that one. So then it's included. Here's some custom attributes that you can have, and that's all defined on your data that you import. Bone attributes is the information for bone deformation, so for applying skeleton. Same with weight. We have a previous weight if we are doing motion vectors, because we need to find out how much our vertex has moved between the last frame and the current frame. Same with the normal attributes. So that's all the inputs that we get on the forward clustered. And then finally, there are a couple of functions defined here, and these are the functions to decode that vertex, that position, normal, tangent, and bitangent. We actually call it binormal here. Usually it's called bitangent, but name's but a name. So you can see that brings in our global state. That brings in our specific inputs for the vertices, basically. Then we have another keyword here, hash globals, that inserts further global state into our template. So we can see here all those attributes. So eventually there's our function. So after that, here we go. Then we get some global state. Oh, look at that. There is our albedo texture. So again, that is it's that guy that's being written. So global in this case is a bit of a misnomer. It's basically it can be some of the global data, but it's basically data that is, I guess, from the global memory. I'm not quite sure why that is called hash globals, but it's again, you need that information. Without that, you don't have access to stuff that you need access to, which again is why we put it into actually this one. Actually, I've been thinking about moving into input attributes, but I don't think we can. We might need to move that into standard includes, actually, because hash globals is, again, both in our vertex shader and in our fragment shader. Now, the next bit is something that is unique to your template. Eventually, we will add an include file for this as well. If you want to piggyback on the built-in template and you just want to expand the built-in template. But for something that does not use the built-in logic, where you want to build a template with your complete custom shader, you don't care about any of the built-in logic, then you are going to need to define some outputs of the vertex shader that become inputs of the fragment shader. So that's why we say here in the comment, outputs to the fragment shader. So we have a vertex interpolated. So we're going to have our vertex. We're going to process that vertex and convert it to view space. And then we are going to output that to the fragment shader. And because let's say that you draw a polygon, there are 3 vertices. As we're rendering the fragments, it is interpolating the vertex information over that triangle. So that's why we call that output vertex interpolate or interpolated. Same with the normal. Same with our UV, same with our tangent and bitangent. And if you compare that, for instance, and I'm not going to go through the whole thing, but I just wanted to show that our built-in shader is quite the same. The order is a little bit different. But here you have also the varying, but you see that we have a UV2 in here. We are outputting a screen position, previous screen position. This is for dual paraboloid, or our dual paraboloid value. I think this one is one that we also do here, right? Yeah, the instance index, that's a flat output. So even though it's called interpolate, it's actually not interpolated, because it's that's actually a value that should be the same for all vertices. And this will prevent it from doing some overhead, which is really cool. But that is actually our index. So when we were looking at, we had that, where were you? So here we have our instance data. Here's our instances. So that's our index into that buffer. So quite important that we're outputting that so that we have access to that in our fragment shader, because we only have access to that in our vertex shader. And then finally, the most important one of all, which is also why the syntax is slightly different, GL position, which is a, well, it's kind of a reserved name in GLSL, but it's only in OpenGL where you get this thing for bonus. In Vulkan, we have to specify it. But that is our GL position, and that is a very important one, like I said, because that is the variable that the rasterer works on. This is how the GPU knows where the vertices are on screen and what it needs to interpolate between those three vertices. Hey, Velhelmer, I hope you're doing well. Okay. So that's pretty flexible. You know, that depends on what you want to have in your fragment shader. These two you can't live without. They have to be there. They have to exist. Here we have a little define just to make our lives easier. We have our global time variable, which is also important because our if we type in I can't get there right now. We'll open that in a minute. If I do something here, let's say that I do something stupid like times time, which will screw up my my shader. I was expecting that to screw up. Oh no, because I'm yeah, multiplying the offset when the offset is 0 won't matter. If I do let's make something funky happen. Do that, then yeah, things get weird because our UVs are now scaled by time, and no, that's not very nice. But that time actually gets processed to be global time, which is then replaced by scene data block data time. Yay! And this is where we start getting into that scene block. So remember when we were in standard include, we have where are you? Am I too far? Not far enough. Well, Wilhelmer, this is we're looking at very new stuff here. That's not even part of Godot yet. So this is almost a crash course into how the shader system works internally, which might be interesting to some people. But now I can't find what I'm looking for. Let's just look for it. Scene data block. There we go. So here's our scene data block. So that's what we're accessing. We're then accessing data. And that is, remember what I was talking about before, data is for our current frame, previous data is for a previous frame. So we're accessing our scene data for our current frame. And then in scene data, if I can find that. Oh yeah, that's separately included. We could see that when we were in here. So we're on our material. We're going in here and we go inspect native code, and then we have to wait for a bit while it compiles all the different versions together. Does anybody remember which one it was that we were looking at? I think it was version 7 or 8. Let's make that a bit more smaller. Is it 7? No, that's still def. 8. Still def. 9. That was probably the one that we're looking at. So here we do have our scene data. And somewhere in here, there should be a time. There we go. Time. So that's the value that we're getting in. And time is a variable that we set at the start of rendering our viewport. That tells us how much time has elapsed since Godot started. And I think that is in seconds. Yeah, I think that's a value in seconds, if I remember correctly. But it has a precision up to milliseconds, I think. It might even be up to microseconds. I'm not completely sure. Anyway, the important thing here is that in our template, that is how we access that time variable. Scene data block dot data dot time, and all we're doing here is defining that as global time, so that is a little bit easier to write. So whenever we need to do something with time, we just have that global time, quote unquote, variable that we can use. And again, it's very important, and I think that will be in here when we finally look at where our user code is injected. Let's have a look. You go all the way down, all the way down. This is like finding a needle in a haystack. A little bit. I might be. Yeah, here's our output to the fragment shader. So here's our main. So we get some stuff that we'll look at in a minute. But here's our user code. So it just injects that. Oh, we removed time from that. Dang, we should have left that time in there. We could have seen how time was inserted in here. Oh well. But it is already important to realize that when we look at the user code, that is not exactly what we have here. It's translated to what we actually have. So our UV interpolation, that's actually the variable that we're outputting. So UV is converted to that. And then for, our UV1 scale, UV1 offset, that's actually, now accessing that material block that we inserted. A little bit double with the brackets, but anyway, so yeah. Okay. So that's just something that's important to know. That's why we define that. Just makes it easier to handle that and have that in the code there. Now we get to our actual vertex shader. So you can see how much more. Well, this is quite short because we're doing those include files. Especially if you look here, you can already see how much code is already added in that you're blissfully unaware of when you're writing a user shader. This is one of the magic bits of Godot, where for normal things you don't have to worry too much about all this stuff. But if you want to customize it, it becomes important. So here's our main function. Here we do again another assignment just to make it easier to access. So instead of accessing scene data block.data, we actually copy that into a scene data. Now that might seem very expensive, but the compiler is able to recognize that that is static data, and therefore this is static, so it's actually behind the scenes. It's going to nicely just keep a pointer to this information. It's not actually going to duplicate anything. Else that would be really bad, because that's a lot of data to duplicate. So that is something to be aware of, that shader compilers are very nifty in optimizing stuff that that you're doing. Okay, similar to that, remember draw call? If we go up here, that was our what we call a push constant. So push constant is a little bit of data that we can communicate to a shader that we don't have to allocate any buffer or anything for. It's just put onto the command buffer, and and as a result, that also has to be a very small amount of data. I think the limit is 128 bytes, but we're using much less. So somewhere here, can't now find. I think it's all the way at the top here. We should have that almost. No, remember scene data was later. Here we go. So here's our draw call. So that's our push constant. You can see that's push constant over there. And all we're getting is our instance index, a UV offset. Not completely sure where that's for. And we have some multi-mesh motion stuff for when we are using multi-mesh. And again, there's actually a couple of things that we're not doing in our default template here that disable some things. Like I currently don't have support for skeletons in here, and I have only half the implementation for multi-mesh in here. So again, you can break things really easily if you don't include everything. And that might be a choice if you want to write a a template specifically to be used for terrain shaders, for instance, which is one part where this can be really powerful. You might not want to include all the logic for bone deformations and all the logic for multi-meshes, because that might even make your shader a lot slower. So it's something that you might want to avoid. Yeah, Philhammer, I'm definitely going a lot deeper than I was expecting tonight. But I do think that it is a really good thing to sort of have a go through this stuff, so that even if it's just something that people can reference later on when they're dealing with these things. Anyway, so whenever we are doing a draw call, we are specifying which instance we're drawing through this variable in draw call. And again, that is then a lookup. And I can more easily look that over here. I've already pointed this out before, but it's better to repeat it. And let me find it. So here is our instance data struct, and here is our array of instances. So with this, we are pointing to the entry in this array for our instance that we're drawing. So that way we get access to our transform. If we're doing motion vectors to our previous transform, whatever flags we have here, I don't know out of the top of my head what they are, but there's a bunch of flags that depend or that define what we need to do with this thing. We have some offsets into our global buffer or instance variables. We'll eventually figure out what that's for. We have some offsets for if we're using GI. Layer mask, that one I do know. That's the layer masks for objects, so that we know in which layers this is being displayed. And that can be important for our culling. Obviously, a lot of culling is done behind the scenes, but there is some extra culling going on here as well. Light map UV scale, that is if we're using light maps, we're scaling the values there. These are very important. This is part of our our encoding of vertex information. And similar with this, we have a UV scale that we're bringing in here because our UV values or source values might need to be scaled. And that is not to be confused with the scale that we have specified here. This is again related to the fact that we can more efficiently store UV coordinates when they're normalized. And as a result, we might need to scale them up. So that's why we have that index here. But as you can see, that if we are a multi-mesh, and here we are actually checking, oh, look at that. That's one of our flags. So we have a instance, and that's actually also a good thing. We should have our flags defined somewhere over here, probably more at the top. So we can see what actually all those flags are. Here we go. Look at that. Dynamic. I think that's a flag that's set if our vertices are modified dynamically, like through bone deformations, but could also be because of our particle system, our trail system in our particle system. Non-uniform scale. So this is a flag that's set if our scale, if the scale that you set on the object has a different scaling for the X, Y, and Z axis. Whether we want to apply GI buffers on this instance, whether we want to apply SDF GI lighting, whether we want to do that, whether we're going to do that, whether this is part of the particle systems, whether this is a multi-mesh, whether our multi-mesh format is 2D or 3D, whether multi-mesh information has color data, whether it has custom data, whether this has a trail shift, it's probably part of the particle system, etc., etc. So you can see that there's a whole bunch of instance flags that are joined together in that. So in this case, we are checking whether our instance flag multi-mesh is set. Now, interestingly, looking at this, that is actually our fix for our bug, why we had lots and lots and lots and lots and lots of problems on our good friend the Quest 3, because if I recall correctly, that was originally this, and that works on everything but a Quest 3. The Quest 3 breaks. If I remember correctly, that was the conclusion out of that. So there was some sort of casting issue where it didn't nicely cache to a Boolean. Interesting. So here we're doing a specific cast, and I think that that Clay even has, and this is again very important, that Clay even has a. No, he's only done that on the mobile renderer. That is why it looked different on the mobile renderer, because on the mobile renderer, sorry, I just want to see this for a second, because suddenly realize that that this is part of this. Where are we? No, I'm too high already. So if we look at the mobile renderer, main, we calculate. So here we're going to draw call index, also in draw call. Scale. Hold on, because that was coming in through a specialization constant. But because there we have now, and I'll come back to specialization constants in a minute. Why is that so far down? But anyway, here that is being handled with a specialization constant right now. And that's the way that we worked around that. So all the specific multi-mesh code is here. I don't know where it was. Here's the end of it. So yeah, that's differently in the mobile renderer compared to the clustered renderer. And that is, again, one of the things that's very important to realize, that this code can only be compiled on the Forward Plus renderer. So if you use this custom shader template on the mobile renderer, things will break. Very important limitation to be aware of. Yeah, but I think that was the problem. Maybe it was even this syntax that broke. I'm not quite sure, because I remember that it was doing something similar or the same as this on the mobile renderer originally. Anyway, it doesn't really matter. What matters here is that we can see that our instance index, we're actually including that by a GL instance index. So our instance array contains entries for all mesh instances. And then when you have a multi-mesh, it will actually, let's say that there's a multi-mesh that draws a mesh 10 times, there will actually be 10 entries in there. When you do a draw call for that multi-mesh, our draw call will be internally repeated, and it's not really issuing separate draw calls, obviously, it's drawing multiple instances, where it's increasing that instance index from 0 to 9 for every instance that it's rendering. And therefore we're adding that to our index to get our individual entries, so that we get our individual transforms, positions and everything like that for each and every instance in that multi-mesh. Here we can see that we're now assigning our instance index to our index inter P, so that is our output that goes into our fragment shader. So because obviously we want, now that we know what the correct index is, we want access to that index. Perfect, working. And here we're just going to copy a whole bunch of information into local variables. And again, our compiler is smart enough to actually not copy, but just know that that is the same value as long as you don't change it. Now, there are some situations where we do change it, but for the most part, these are not actually copies. We just keep a reference to the actual original. We are doing that just so that we have an easier name to work with. But here again, we can now see that from that data, from that instance data, we're getting the transform for the instance that we're currently rendering, putting that into model matrix. Model normal matrix, here we are checking that uniform scale. If we are non-uniform, we do a transpose to make sure that our normal is correct, because it can't survive that. But if it is uniform, we just use it as is. We just get part of that model matrix and we put it in there. We make a copy into read model matrix. It's a little bit too much information to go into why we keep making that copy. if I remember correctly, it has something to do with the motion vector logic that we do. But that is the data that is actually exposed to the user shader. So, whoops. If in this code you would be using the model matrix, it is that read model matrix version that you are accessing. We are copying out our invoice view matrix. We are copying out our model view. Now these names are very important. So this is not just copying from the source into the destination. So here we're actually doing a calculation, right? We're multiplying the view matrix with the model matrix to create our model view matrix. Same with the normal matrix. We are putting it in model view matrix. These names are very important because these names are exposed in Godot to your GD shader. If you do not name them like this, if you give them different names, your template will work, but you will not be able to access them in your GD shader. When you access the model view matrix in your user shader, it will throw up an error and it says, hey, I don't know what model view normal is, because that's what it's using internally, because that variable doesn't exist in your template. So that is something where you have to be very aware of, that a number of these names or many of these names are fixed. And unfortunately, the only way that you really can get a listing of that is if you again go to the source code. So in this case, we need to actually look at this file called the shader scene for mobile CPP. And then, so that was at the top. Yeah. No, that's our entry point. So it's not in here. It's actually, let's go and find it. Model view matrix, for instance, as an example. These are all our default ones. Yeah, it's in here. So this one, that's for class 3. So that's for the compatibility. And we need to find that in our, here we go. So it was here. I was looking in the right place. Sorry about that. But yeah, here we can see, no, that is not what I'm looking for. I'm looking at the renames. It was further down, all the way down here. So here we can see all those renames. So model matrix, if that's the keyword, that is converted to read model matrix, model normal matrix, model normal matrix. So these variables, if they don't exist in your template exactly in that name, then if these are used in the user shader, you will get an error. So that is something that is important. Let me catch up on chat because there's a bunch of things. Hey, welcome back, Dev. One last quote. Should I make it as an issue or proposal? Yeah, if you're talking about your different material per viewport thing, that should definitely be a proposal. I think Yubi already answered that. And yeah, the Discord is a really good place to discuss what exactly you want to do so that you can get a more complete ID and as a result, get some help writing that proposal as well. Noobs Gaming, I wish I had the head to understand shaders well. This goes way beyond that. Like I really stressed at the beginning of this stream, obviously anybody who just wants to know about this, you're welcome to view. You probably learn something about how the internals of Godot work. But this goes far beyond what the user shaders is, so far beyond what it is that you are writing here. And this is definitely, targeted at people who, who really want to understand and do stuff with the core of the shader system in Godot. Anyway, bottom line is you need to make sure that those variables have the right name, and any variable that you do not have in your shaders here obviously is going to fail if someone uses that in their user shader. And you might do that on purpose, right? You might not want to support everything. You will actually see, in here we actually defined a whole bunch of things that we actually intend to use But in the fragment shader, I have defined a whole bunch of variables just for the sake of having them there so that the materials don't just fall over. And even with this, I've left a few things out. So there are a number of variables that if they are used in the user shader will just give a compilation error. And trust me, that compilation error is not fun because there isn't really very good output to help you find that. You really almost have to, like I'm doing right here, run everything in debug mode so that you have better access to the logs and stuff like that. Anyway, that is only something that is important to the person who writes the templates, and they need to be careful. Yeah, absolutely, Cubichet. If you define global uniforms, they are pushed into, where were we? So if we look at our standard inputs, there was a global buffer here. Here we go. Global shader uniforms. So in this, our global shader uniforms are being injected. And I don't have any, so you won't see any, but friendship ended with world environments? Why do you say that, QB? Oh, what am I missing? Anyway, if we had those, we should see them somewhere in here, but I don't think we have any. So, but somewhere in here, we should have, yeah, global uniforms. So if we had any global uniforms, we should be seeing them in here, which then also gives us more information about how to access them. Custom forward fog. Yeah, you can do your complete own fog implementation in this if you want to. Absolutely. But again, I can't stress enough, because me and Clay are planning to strip this whole thing apart and completely rejig this so that you actually have, these 4 include files are only the beginning. Eventually we'll have includes for almost all the standard built-in logic, and hopefully we want to get to a point where this scene for cluster GSL is a bunch of includes at the beginning, a very simple main function, and then the same with the fragment shader, a whole bunch of includes, and then a small core, so that you very easily can add some logic without losing all the built-in functionality. Right now, with what I'm doing here with this one, we are building a complete shader system that does none of the cool things that the built-in shader does. However, that might be exactly what you want. Obviously, if you want to do something like custom forward fog, or you want to do something like your lighting, your post lightning calculations for a toon shader, you want to have that work that Clay and I are planning to do in the near future. But if you want to do a really optimized, much simpler renderer than the the whole PBR renderer with all the bells and whistles that are in Forward Plus, then this would be the way to go. You would actually write your own thing. Anyway, so we have our matrices all defined, and then we do our inputs here. And again, I do have to stress, I didn't put them all in here, so there are a couple of, so for instance, UV2 is missing here. So if I use UV2 in my shader, big shader error. I can actually, let me actually show that, because just to scare everybody, if I put in here UV2, UV2 is UV2 times 2, and I wait until it compiles, and boom, we get an output of our whole shader. We get some other errors. It's probably going to give them for every frame that it renders, and somewhere off screen, that I can no longer read, is my error that that I actually want to see. But because this is so big, I can't actually see it. And it even becomes really hard. I really need to wait now until this disappears. Come on, disappear for me, please. Like, here we go, like, please. Probably because I'm hovering above it, it doesn't do it. Okay, do not hover your mouse above the error. Now I can remove that line of code. Boom, so that it compiles properly. Here we need better. Well, yeah, and I can actually go to the logs here because I'm actually running it in VS Code's debugger, so we can see all the output. And if you scroll all the way, this is actually kind of nice because it does have the right info. Because if I scroll all the way up to the top, scroll, then here's the actual error. Oh yeah, and of course it is compiling 20 different variants, so we just have our error reported 20 times as well. That's the other problem that we have here. But it is nicely saying here, failed to parse, UV2 interpolated is not found on line 823. So if I now scroll down, and further down, and down here we find line 823, we find that UV2 interp. And again, we call it UV2 in our user shader, but it gets translated to UV2 interp in our actual shader. But that is our line of code that we just added. And it's saying, I have no idea what that is. Why doesn't it know why that is? Because I'm dumb enough not to implement it into my template. So, yes. And I might eventually try my best to make this test template as complete as possible so that it has everything in there, whether we use it or not, but that at least you have the basis in there. Yeah. That kind of goes outside of the idea of Godot is free. I don't think those mouses are cheap. Anyway, so luckily we made a function for this, and you just need to know that you need to come to call the function, because like I said, our vertex position, our normal, our tangent, and our binormal / bitangent, they are packed just to save a bunch of space. We're taking almost half the amount of data, which means less bandwidth waste, which means faster shaders. It's actually cheaper to unpack them than to increase your buffer size double and get cache issues. So okay, Wilhammer. Mental note: don't get that mouse. So how it actually unpacks it, we don't care. That's nicely implemented in that function. We just need to know that we need to call that function, and it will take our angle attribute as an input, our tangent attribute as an input, those two variables that we had in our instance data as an input, and it will output a normal, tangent, binormal, and vertex. Do note that there's a bunch of if-defs here, that we optimize this code and remove stuff out of there if it's not actually used. So if we don't use the tangent and binormal, we don't waste time unpacking those. We just skip that. We just only unpack the normal and vertex, or in the most optimal case, we only unpack the vertex. So that is why it has that weird sort of notation. One of the things that we're thinking about is eventually turning this into a macro, so that you just add the macro there and it just inserts that bit of code. So again, the more we can remove as knowing, exactly the syntax of calling something, the easier it becomes to use the existing logic to create your own versions of that. But that's, again, future music, where we plan to make it easier to bring in the code that basically is the same for every template that you implement. Same here for UV. For the UV, we get our UV scale from our instance data, and if that UV scale has a value, we're just scaling our UV. Now we're only doing that for UV1. We're not doing that for UV2, because we're assuming for UV2 that is either we're not packing that one, we're not compressing that one, or we're assuming that's always a normalized value, because it's generally used for light maps and things like that. So it's usually not a tileable value. not completely sure what the decision there is. But anyway, so we are doing all that. If we have an override position, that define is set whenever position is used in your user system. We just define that variable because we need to do it. And now the magic. That syntax here, hash code vertex, that tells Godot this is where our user's vertex code needs to be. So here is where we, we're on 20 windows, is where we insert this bit of code. And I'm not going to run through that whole big window again because we've seen that a few times already. But that's where our user code is being inserted. All right. And then finally, we have a little bit of output. All I'm doing here is I am converting my vertex into view space, doing the same for my normal, doing the same for my tangent and bitangent. Here, if I've got override position, I'm just assigning it. Else, I'm calculating it by applying the projection matrix, and we're finished. Now, again, this is as simple as it gets. We're throwing a whole bunch of functionality overboard here. In shaders, I can define that I actually want my vertex in world space, in which case I should be calculating the vertex in world space here and then only multiplying with our view matrix here. I've left that out of my template. I wanted to keep my template as simple as possible. So this template does not work with all render modes. And in this case, that is a conscious choice. I specifically said I want to only use this in these conditions, so I'm going to skip over that option. If I want to have a template that works in any condition, I need to duplicate that logic. And again, that's the difference between having a setup here from about 300 lines instead of having over 2,000 lines of shader code. It's just because I'm leaving out a whole bunch of things that I don't want to support right now. And that's again, that's a choice. The more you want to support, the more you need to look at what is actually implemented in Godot itself so that you can follow through and make sure that that you support all the different options. With that is our fragment shader. Yeah, you could do that as well, QBShare. You can change your template in such a way that you force that you do all the calculations up front, and by the time that your user code runs, everything's in world space. If that is something that that you think is useful, then yeah, you can basically make it that way. So I think you could even go as far, and this is one of the things that I am really wondering about. Whether that makes sense is that we actually have a vertex local, vertex world, and vertex view at the beginning, and that it's no, we don't have custom render modes. It's more about ignoring render modes and just hard coding a certain mode in here. Like right now, we don't support world space render modes in here, but you could also make it force that. Right now, there is no way yet, and this is probably an enhancement on this system for the future, but there is no way yet to define additional things that we want to do here. So if we want to do something like my render mode, that should give a nice error. Yeah, don't know my render mode. If we want to be able to do that, we need to add some system that we can actually trigger that define that we want. And I think it's completely possible. And the same with, we want some new variable is blah. If you want that, and this should be a variable that is specific to my template, that's something that I do want to support at some point in time. But at this point in time, we don't have a way for the template system to register those additional metadata to the shader compiler. And again, that's that's something that would be a nice improvement in the future. But that's not something that we'll likely do in the very first version. Yeah, in theory, it's not hard because it's we just register that value. The problem right now is that the way that it currently works is if I would register a render mode or I would register a built-in variable, it would apply to all templates, because right now the shader compiler has no idea that we've introduced the ability to have different templates. So there needs to be a new level introduced there. My cat's being nuts. Misty, what you doing? Are you going to break my son's racing chair? Something hiding underneath. She's chasing something or trying to grab something. That's funny. Cat life. Okay, so yeah. So in theory, it shouldn't be hard. In practice, I think there's going to be a few niggly bits that are going to make life a little bit hard. But I think we'll get there. Yeah, unfortunately, my cat doesn't like it when I pick him up. Also, I'd show him to you guys because she's very cute. So with that, we have our Vertex shader done and dusted. So let's go and have a look at our Fragment shader. And a lot of this is very similar to the Vertex shader. So a couple of things I'll try and go through very quickly. We again have our GLSL version up at top. We have our hash version defines. This is obviously the exact same version defines as we have in the Vertex shader. I don't know if it actually, that's actually interesting. I'm not sure if it is exactly the same code or if there are things that it does that are specific to the different shaders. You are chasing a piece of paper, cat. It's just a piece of paper. What are you doing? Is that fun? There we go. Okay. So I think this is the one that we were doing. So we're in our Fragment shader now. So this is, for instance, stuff that was just added. So if we go into a we can already see that, yeah, they are exactly the same at the top. So we're getting the same information injected here. We have our same defined shader as sRGB. And again, right now it doesn't do a whole lot, but it will be important once we start exposing more include files that contain functions that will have, you know, and this is probably more important in the Fragment shader than in the Vertex shader, but it can still be interesting to make sure that the right sRGB conversions are done. We're including the same standard includes. So we've already gone over that same file because all that global information we want to have available in our Fragment shader as well. But here's a new one, specialization constants. Now, here's where it gets a little funky. We could actually include this in our Vertex shader as well. We're currently not using it in our Vertex shader. We are on the mobile platform. There's one specialization constant. Well, we just looked at it, the multi-view one that we are using in the Vertex shader. But it's one set of constants that, so this is not shader dependent. It's one set of constants that we define. And specialization constants, just like we have, you know, we have these 20 versions here that well, there's even more, 24 versions of the same shader here for all the different use cases. Within those 24 versions, we can create even more specialization, more versions through our specialization constants. Now, when we look at that, we don't need you anymore. When we look at that include file, we'll see that there aren't that many. We have one here, and then obviously we have different ones for our mobile renderer. In the compatibility renderer and OpenGL, specialization constants don't exist. So they're actually emulated, and the syntax is different again. So again, this is one of those examples where, you know, if you write a template for the forward plus renderer, you can't use that template on any of the other renderers. These are things where things go different. So yeah, so we have some more constants here, whether we're using forward GI, whether we're using light projector. So this is basically something that becomes true if any of the lights that are related to actually, yeah, I think if any of the lights for that instance contain light projectors, or any of the lights that are shining on that thing, then that becomes true, and that enables a whole bunch of extra code. And again, that's just an optimization, because if a light does not have a light projector, or if there's no lights with light projectors, you can take out all that code, and that means that your shader runs faster. Whether you do soft shadows, so this is pretty much something that will just be on or off. Same with directional light, so that will define how good your shadows look. Here's some constant values that we bring in. Whether you want to use mipmaps on your decals, whether you want to use mipmaps on your light projectors, whether we're using fog in our shader. So these are, again, things that can toggle on or off bits of code inside of the shader. But in this case, they are actually toggled inside of the GPU driver. And that can be, if that is properly implemented on the driver, that can be faster than creating all these different versions on our side. But at the same time, these have limitations because of the way that they are compiled in to our define approach that we use here. So it's another variation of something we're already doing. For you as writing one of the templates, it's just important to be aware they exist, because you might want to switch on or off certain functionality in your shader. But generally speaking, if you are using any of these, you will be using them through including built-in logic. And again, that is something that is still future music. That's still something that's coming. So be aware that they exist, but likely at this point in time, not really that important. Output buffers. Those are very important because that is what we output. So in a normal situation, the only thing that we output is a frag color. So obviously, when we are rendering our view, we are, we're just writing a color to the buffer. When we are rendering to shadows, generally speaking, we don't have any output at all. To be exact, the most ideal scenario is that we don't even have a fragment shader in that case. In reality, there are always some situations where we will have a fragment shader. For instance, if we want to do an alpha scissor and apply that to the depth buffer as well, then yeah, that's important. Or when casting shadows. But there is a performance penalty for including a fragment shader in the prepass. Now there are some other modes that we have, and here again we are switching on all those defines that we talked about all the way at the beginning. So like I said before, if render mode depth is set, that means that we are dealing with the depth prepass, or we're dealing with shadow maps. So this is all applicable. Applicable to shadows and prepass. While this is applicable when we are not there. And basically, if we are rendering out color, we only have two options. Either we are rendering to frag color, which is our normal thing, or we are separating out diffuse and specular, where diffuse is basically your output color, but we're writing specular separately. And that is important for, I think if you do screen space reflections, that's the situation where we do this, because that's then later combined, because we only want to do the reflections on the diffuse buffer, not on the specular buffer. So the specular buffer is applied after screen space reflections. There's probably other situations where we do this as well, but that's the one that I remember for the top of my head. Render material, from what I have been told, because I haven't really looked at that one before, this mode is used when we are rendering light maps. So that's a very special case. It's not it's not really a def pass, but for some reason it's part of that. But here we're splitting everything out in its components, almost like we're writing out a G buffer. And if I ever get to it, secretly still got plans to do it over a weekend or two, to finally do a deferred renderer. In that case, it will be on this side. We will have a similar output into separate buffers, splitting out the albedo, normal. OEM stands for I think that is AO, reflection, and metallic. There's another variable in there. I think it's probably. I think it's in a template. We'll talk about that. Emission, separate output, and then obviously we are writing to a def buffer, but we have a separate def output where we're actually writing out the unprojected depth, which interesting that we do that here. If we're not doing that in normal situations, we then have the ability to write out normal and roughness. So in our def prepass, we can do that, in which case we are running a fragment shader. So that is a performance penalty, but it means that we have roughness and normals in a separate buffer that we can use in some of the lighting functions, which it can be very useful. And then obviously we also have the ability to output to a GI buffer. Now, I've never looked at the voxel GI implementation, so I can't tell you how that works or what should be in there, but it's in there. And at the end, we have optionally, regardless of whether it is def prepass or not, although I believe that this is only going to be ever set if we are doing the normal the color pass, so the normal opaque pass, is being able to write out motion vectors. So this is important, you know, when motion vectors are needed. So with TAA or FSR, or you know, if you have a compositor effect with motion vectors, yay, then obviously that is enabled, and we have motion vector output, and that isn't something that you need to actually do something with. So that include file adds those all in, and that's why we have it there, because that is really static. You don't really have control over that. Here's our hash globals again, so that's going to bring in some of our our global state, and this not to be mistaken with global uniforms. We found out. Still find this a weird name, seeing that contains our texture inputs and all that sort of jazz. So these are what we basically copy from our normal built-in template, but then obviously this bit is dependent. This should be an exact mirror of what we did here. So here we defined what our output is of our vertex shader, and then therefore becomes our input of our fragment shader. So in our fragment shader, we need to define exactly the same things. So these locations need to match. But now we say it's an input. Obviously the types need to match, and then you tend to use the same name. It's kind of nice. But that way, you can define what's coming out of your vertex shader. And like I said before, you got your 3 vertices, you're going to draw your triangle. So obviously all those values are interpolated so that for each fragment, you have the right value, with the exception of this one, which is defined as flat because it's supposed to be the same for all 3 vertices, which is our instance that we're currently rendering our polygon for. We also do our same define here to make it easier to access global time. Again, also important because that is what time maps to. We again, do our copy of our scene data. Like I said before, it's not actually copying. We just get a reference there. It just makes the code a little bit more readable. Here we go and copy from our input our instance index into a local variable. Not strictly needed. We could be using that directly, but makes the code a little bit more readable. So here we get our vertex from our interpolation. We get, we calculate our eye offset from our scene data using our view index. So this is if we do stereoscopic. If not, we do not. But we also calculate our view direction. So that view direction is the ray going from our eye to the fragment that we're currently rendering, which is going to be very important in a minute, because that is the is that would only be important if you do specular, but we're not going to do specular. So forget that I said that, but there are a number of situations where that is very important. All right. we get our normal, but we normalize that because as we interpolate that normal, it won't stay nicely normalized because it doesn't do that automatically. So we need to do that. Do side check, again, a definition whether and this I think is related to our what am I trying to think of, our cull mode, whether we are culling back faces or not. If we're not, if we're displaying either side, we want to invert our normal when our normal is facing away from us. So we're not front facing, we're back facing. We're going to flip our normal around so that both sides of an object are properly lit, because we want to have the side that we're looking at lit. We then get our binormal and tangent, but notice that if this one is not used, we set them to 0. And I'm not exactly sure what scenario that would be valid in, because if it's not used, then we shouldn't need them. But there's probably a reason why I copied this bit out of the built-in shader. All right, QB, thank you for joining. I hope you learned something. And you know, this video will be online for as long as my channel exists. So hopefully that's a long time. So if you ever want to watch the rest, then feel free. We bring in our UV. Again, notice that we don't have a UV2. So if you want to be absolutely complete, we should be adding some support for UV2. We're preparing some outputs. So albedo, emission, and alpha are the only one that I currently support. I do process our normal because we might do something with that at some point. Actually, we will do something with that one. Very good, QB. I'm glad that you enjoyed it. But then there are a whole bunch of extra ones that I define just in case we need them. And then a whole bunch that I define that I don't support in this. Oh, there's our UV2, by the way. But I'm only putting them in there here so that if it is used, we don't get a big error, even though that the functionality is disabled. And again, you know, for all these, it all depends on whether you actually want to support them, whether you would actually do something with this. So you can see that I'm ignoring metallic and specular. I'm ignoring roughness here. So all those things I don't do anything with. And we're not going to do anything with tonight. So actually, it's already 11:30, so we'll see how far we get with Ultima. I might have to turn this into 2 streams: one stream explaining everything, and one stream actually implementing some stuff. But we'll see how far we get. Here's our magic again. We are inserting our fragment code over here. So here, I can't scroll down to that, but our fragment code over here, I can close you again. That code will be inserted over here. And that's what that does. You can see that at this point in time in our do lighting, I'm checking for render depth and unshaded. Obviously, we don't want to apply our lighting if our render mode is unshaded. We don't want to apply our lighting if we are dealing with, you know, our depth prepass or our rendering shadow maps. But if we do a little bit of normal calculation. And then here, you know, I'm inserting our light function, but right now I am doing it in an if false block. I'm ignoring that because I don't have any of the structure in place to actually make this work. We're not looping for any lights here. So I've just put this here as a placeholder. And to be honest, for what we're doing, or what I'm planning to do in this template, we probably don't even want to have that in there. So I'm probably going to leave that the way that it is. So this block of code is only added if we are doing lighting, and currently it doesn't do anything. Here's just the alpha scissor that I put in. There's a bunch of other alpha scissor modes that Godot supports. I've only copied this one in. I've left the other ones out. But again, if you want to support all of them, there is more code that needs to be in here. But I wanted to keep this somewhat succinct. Didn't want to have everything in there. I did have this one, which is a special alpha scissor for OPEC pre-pass threshold. That's a mouthful. That's specifically for rendering depth pre-pass, and I think actually more important for shadows, where you might want to, where you still want to do a transparent material in the opaque pass, but you want to do an alpha discard for those. And that threshold might be different than the alpha threshold here, because you might want to cut that out differently. I don't know the exact use case for this, but I know that we have that. Don't make no issue. Okay. So this part, this last bit, completely mirrors our output buffers. So here I'm checking, again, the mode depth, same as here. Mode material. If it's mode material, I am outputting what I need to output here. So you can see here I'm doing alpha, beta and alpha. This one's actually not correct. There was another function that you need to do here, but I've left that out here because that is a function that I want to pull in through an include file, and we don't have that yet. So I just have this as placeholders. I'm not expecting anyone to use this for building, baking light maps anytime soon. But here, oh yeah, here we have all the things. So it's AO, roughness, metallic, and subsurface scattering, I think it is. The strength of that is written out. We have our emissions being written out, and we have our vertex Z being written out to our depth buffer. So while right now I don't think this will ever be used, it's in there. This one is more likely if this is used in combination with other things. So we're writing out our normal, and well, we don't have a roughness here. I could actually probably be a bad idea that even though we're not doing anything with roughness, is it actually put that in here, and roughness 1 is probably better anyway. So that's a good little fix. I'm just blanking out the voxel GI buffer if it's needed because I'm not doing anything with voxel GI. But then if we are doing a color pass, we're either splitting our albedo into diffuse and specular. Now this needs to change once we actually do lighting. And the same for fragment color. Now we're just putting albedo in here, but we actually want to obviously put our light value in there. So we will eventually end up calculating that one. I don't know if we have anything in here that's no, because that's actually no light function. So so I probably want to define some variables there, but we'll see. Okay. Well, that reminds me, one of the other things that's very important to know, even though we've defined all these things here, if they're not used, they're not part of our user code, the optimizer will just remove them. They won't take up memory, they won't take up overhead. Anything that we put in here, any variables that we define that is never used in code, that doesn't have any bearing on the output. It's even smart enough that even if we do calculations with it, like for instance here we're doing calculations with the normal map and the normal, if we then proceed to never use the normal in our light code and never output a normal because we're doing a normal fragment output, it will all be optimized out. The shader compilers on the GPUs are very smart nowadays. They will remove any what they call dead code very nicely for us. So we can be a little bit liberal and a little bit careless with some of the stuff that we're doing here. Obviously everything that does survive, we have to be aware that things will take up registry space in the shader, and the more variables you use, the more chance you have that you run out of space and things become slow. All right, with that, we are at the end of describing everything. And we are, how long has the stream been going on? This took way longer than I was expecting. I don't know. It's now 11:30. We started at 9. So 2.5 hours in, something like that. Okay. No, not bad. So it is nearing midnight here. Let's do one more thing. Let's just at least start adding in our directional light logic. So the first thing that I want to do is I actually want to duplicate. Where are we? Oh, that's just going to be copy paste, I guess. Let's just create a new file and just copy that over. Will you not do that, please? There. New file, and we're just going to call this LdotN template. Boom. And I'm going to copy you over. Copy, paste. Boom. All right. So now we have a new template called LdotN. And again, like I said before, LdotN is like the simplest of the simple lighting calculations for diffuse light. And we're going to start with doing that, but we're just going to do this on directional lights. So that also means that we're going to need to do our ambient lighting. All right, so one of the things that we need to do here as well. I might want to change this a little bit. I'm actually going to split this out. So I'm going to make this if defined, no, if not defined, mode render depth. If not defined, unshaded. Boom. And I kind of like putting this here so that I don't lose track of what we're doing. And if not unshaded, and this is going to be, and if, actually, let's leave those out. All right, because I actually want to put an else in here. There we go. So what we're going to do here is, if we're not in a render depth, we want to have a ambient. We want to have a diffuse. And we're, in this case, not going to do specular. Normally we have specular in here as well, but we're going to leave out specular calculation. Then what we want to do now is, if we are unshaded, maybe we do that the other way around. I think that would be nicer. So we're first going to check if we're unshaded. We're simply going to say diffuse is albedo, which means that here we're now going to set this is diffuse. I think it's actually, in this case, this will just be ambient plus diffuse. We're always going to add ambient in. And we're also going to do that there. Now, the thing that we're missing right now is emission. Do we always want to put in emission there? Or do we want to do another calculation with emission? I'm going to ignore emission for now. We're just, I don't want to be distracted with dealing with emission at the moment. Then obviously we're also going to go and do that here. But, oh no, here we're never going to have lighting. So we're going to leave that on albedo. So it's purely that and that. It's going to be there. But in this case, we're going to say if it's unshaded, then nothing. So let's start with our ambient calculation. And that one, I am going to have a look at what our cluster shader does. Now we have to find in this big mess fragments without the hash, or the hash at the beginning. Yeah, the other way around. So now we can go down all the lighting calculators. So again, like I said, we're going to all move these into includes. so that we can actually do stuff. Now here we actually have a fragment shader that is called from main, but you know, it's still the same sort of thing. So all these calculations, you can see there's a whole lot more variables that are being defined. We're doing, you know, stuff with double precision that I haven't even added into our template. Here's our fragment code being done. We have stuff with light transmitters that we're going to use. So this is a light vertex thing that's then copied back. Can't remember the exact situation, but it's a bit of a, excuse me, it's a bit of an exceptional case. So I'm not going to worry about that here. Oh yeah, in that case, we are also going to recalculate the view. Oh yeah, that was, I think that was to do with the logic that if we are doing a modification of the vertex, if we're doing changes to that, we want to do some extra logic there. Anyway, that's all good. So here's all our alpha scissor logic. So there's a lot more logic in there. I'm going to nicely ignore most of that. So here's our pre-pass, that one we do have. Here we have that our normal is updated by our normal map if we have a normal map in there. So now our normal is a normal with normal map applied. Well, we're not going to care about anisotropy. Can't even pronounce that one. I don't know why there is an extra clip here, but probably is a reason for that. Okay, if not defined, render depth. Are we going to do fork? Well, I'm going to skip over fork today. Would like to add that in. Decals. Definitely want to do decals at some point. So maybe if I do it on the stream tomorrow or whatever the next stream is, we might add decal support to our thing. But for now, we are going to skip over all of that. Here we start with our lighting. If normal use, we do a roughness there. So we're ignoring roughness right now, so we don't care about that. Here we can see that we're starting with a diffuse light and ambient light. We just call that ambient and diffuse. We also have specular. So here we're actually going to start with our actual logic. So our decal is actually altering our albedo. That's interesting. So that's kind of cool to know. Oh, and even our emission is potentially affected. That's nice. Anyway, that's something that we are going to look at eventually, but not now. If not defined, we are going to do, so that's if we have an emission, but we're not caring about emissions right now. But eventually our emission needs to be multiplied with something. And here we actually go to our real logic. So interesting that we have already some stuff here, even if we don't use it. So the first thing that we're going to do here is actually using our reflection cube map. So this is for reflecting from our sky. We're going to skip over that today as well. But I might make a remark here that we might at some point to do reflection cube map. Sky. So we might look at adding that in there as well at some point. Why is my thing set wrong? There we go. So we're going to skip over that logic for now. All right, cool. We're going to skip over the light mapping code. You can see there's quite a bit of stuff for light mapping. Okay, still more light mapping stuff. Where is this? Not light mapping. I'm looking wrong. This is if not defined light map, which we are going to go and do here. So here we're just going to go and put a sudo get ambient light. Okay, so here is actually our ambient lights. Cool. So if scene data, use ambient lights. Cool. And maybe just to make our life easy, we're actually going to call that ambient light and diffuse light. Let's do it here as well. Ambient lights, and then diffuse lights. And I'm purely doing that because if we are going to copy some of the code over, it helps not making mistakes by leaving that. Anyway, our ambient light is just coming from there. Okay. Now, interesting enough, why is that not being multiplied with... let's see. So if we're using a cube map, so this is actually coming in from a radiance map. So that's something that we are going to go and not care about right now. I want to leave that alone. Okay. There we go. And the funky thing is, if I remember correctly, okay, we didn't do anything with customer radiance. We are not going to do anything with clear codes. So we're not going to do anything there. Okay, cool. And then light map. So we've just got our base lighting come in. Let's use light map. What is this all about? Oh, that's SDFGI. No, we're not going to do anything with SDFGI. So let's skip all over that. Okay. Now we're over here. Screen space effects. No, we're not going to deal with that. Reflections. So here we get reflection stuff. We're not going to deal with reflections at the moment. And now we finalize ambient lights. Okay. And now we get it. If it's disabled, we're just going to ignore what we just did. And the thing that I was looking for was this stuff. Now, here we're actually going to go and multiply our ambient light with our albedo to actually give it the correct color. And we do that also with our AO, which is our ambient occlusion, which I think we can use just as is, because if we don't have ambient occlusion, because we're not getting it from anywhere, it should be in here somewhere. AO, look at that. Then we can just keep it as is. So there we go. So now we're getting it from light map. And that means that we can now apply our ambient lights. Or finalize our ambient light, I should say. Now, one of the things that's really cool is if ambient light disabled is defined, and actually, can we just call that like this? I like that better. If our ambient light is defined, and therefore we are resetting our ambient light to a constant value, and we're ignoring what happens above, the shader compiler again will remove all the dead code above here. It'll be nice to do that. But else we are just going to calculate or multiply that by our albedo and our AO. So obviously this will color our ambient light correctly for our albedo, and this will apply our ambient occlusion if we have an ambient occlusion value, and that is only there if it's been assigned in our user folder. So this is not for screen space ambient occlusion. This is if we have an ambient occlusion texture map in there. And if we never set that, that value never gets a value. And it should be smart enough to not do anything with that. So now let me double check. That's ×1. So it should just filter that out. Really cool. Alrighty. Where are we? I'm scrolling too far. There you go. So with that, we have our ambient light basically calculated. So now we need to start looking at our diffuse light. And we're still going to steal some more from here. So we're not going to care about any of this at the moment. We're not going to do any of the screen space stuff. So I wonder why this is done after we apply AO there, but maybe we do AO slightly different for diffuse, but I'm going to ignore that for now. We have some extra tool logic here, which we're not going to care about right now. And this is, I think this is just for specular light. Yeah, so we're not going to care about specular light at this point as well. So we could add it in, I guess. But we're going to nicely ignore that. So here we're packing some stuff for some reason. Not quite sure why we're doing that, but we probably have a good reason for it. Lighting. So here we're going to actually do our lighting. And right now we're just going to concentrate on direct lights. Okay. And we're going to ignore shadows at the moment. So, and we're definitely not going to do all this stuff here. We're going to keep it much simpler. Here you can see how complex the shadow calculations are. Where is the else if for that? So here's the end if. Okay. So here we're going to go for the logic that I'm actually looking for. So hold on, I am going to go and copy this bit, which is directional light. Boom. That's just to help us. I think so. We're obviously going to do our normal map here. That's fine. And we probably actually want to go and move this more up if we do want to eventually do specular stuff. This is probably good to have at the top here so that we can actually have that normal available earlier, which is kind of cool. So directional lights. That's good. Now we have a maximum of 8 directional lights. And what we're doing here is that we're looping through all 8 of them. But the moment that we get above our light point, we are breaking. So we could do I is 0, I smaller than scene data directional light count. But this actually allows us to do something really cool. I'm going to copy a little bit more while I explain the rest of this. Because what this allows the compiler to do is when we compile, we don't know how many lights we have, whether we have 1 light or 5 lights or 10 lights or whatever. So if we would put this directly in the for loop, that means that the shader actually has to completely loop through that for loop. If we don't, if we have a constant like this and we say it's 8, if the shader compiler decides that it's faster, it can actually include 8 blocks of the same. It's actually going to repeat this 8 times. And it might seem really weird, but it's actually faster for the for a GPU to execute that. Or so I've been told. So as strange as it seems, this is actually faster than putting it directly in there. Now, the second thing that we're doing here is that we're comparing our directional light mask to our instant mask. The directional light buffer will contain all directional lights that we have, whether they are applicable or not. And therefore, we have to check if this directional light affects this instance that we are rendering. And we do that by checking the mask. If those masks do not overlay, then this directional light is not shining on this instance. Not because it's not in, in the neighborhood of the instance is hidden by something. No, it's because we have said through our layer masks that this instance does not get lit by this light. And if so, we just call continue. Don't go. So here's a break. We stop the loop altogether. And here we continue. We just go to the next iteration in our loop. Okay. So now we're going to simplify things a whole lot. We're going to not worry about most of this, because here we're going to go and do our simple LdotN calculation. So N we already have. That's our normal. Now we need our directional light direction. So that's going to be somewhere in our directional light data. How do we know that? We need to, well, we can either go obviously here and do our inspect native shader code. That's one way to do it. And then our other way to do it is just to go in here and go into input attributes and then find where our directional light is. Now I think that is another include that we have. Why am I blind? No, because I'm looking at the wrong one. I need to look at standard inputs. Here we go and look at directional lights. I think I'm already too far. Instances, yeah, it's a bit above here somewhere. STFGI, no. Decals, light apps, it's one of these. Directional lights is directional light data. So where is directional light data defined? Well, that's in our light data include file. Okay, so our light data include file, where are you? Light data include, here we go. Directional lights. So we have a direction variable here. Well, that sounds pretty nice to have. So let's make our life easy. That's a vec3. So I'm going to say vec3 is directional lights dot data dot direction. Now that's the direction in global space and world space, and we need it in view space because our normal is in view space, which means that we should be able to just do, where's our view matrix? Do we have that here? Not those. No, then we need to go up here. View matrix. We don't want our inverse view. We want our view matrix. Where are you? Yeah, so that's going to be scene data view matrix. That's interesting that I'm using that directly. Yeah, that's right, that I'm using that directly. Well, we could make that normal in world space as well, whichever way you want to go. But for now, I'm just going to do our view matrix. I'm trying, is that view matrix or inverse view matrix? I think it's actually inverse view matrix to get this in view space. Or no, we wrap those around. That's right. Because it's the inverse camera matrix is the view matrix. I always forget that one. That means that we need to cast this to a vec. No, we actually can, because we only care about rotation. So we can actually do map3 view matrix times direction. So that gets our direction in that. Now we just do a dot product from that. I believe that's just direction, comma, normal. There we go. And that means that we can now do diffuse is albedo times, oh, that's wrong, dot is dot times dot. That probably doesn't, let's call that LdotN, because I think that's going to complain it being a reserved name. So that's our LdotN calculation, and now we do our LdotN. So we're doing that for everyone. So obviously we want to add that in, because if we have multiple lights, we add them all together. And one thing that we probably also want to do in here is that I believe we have an energy factor here as well. Oh, and we have a color of a light. So I think that those are nice. I don't know why there's a size for this. That doesn't make much sense, but I am going to say that this can then be... let's actually write that out. So we're going to have, is it a vec3 as well? It's a vec3. 3 lights color is that, and then vec3 lights. No, that's actually not a vec3, that's a float. Lights energy. Oops, and that is then dot color. And that is dot energy. Shall we be completely consistent and call that light direction? It's a bit overkill, but hey, why not? So now we can do this times this times that times lights energy. There we go. Sweet. So obviously this is much more primitive lighting calculation than the whole PBR thing that we're doing. This is, we're talking about 1990s light calculations here. It's as simple as you can get it, but this should work. So now that we have that as a template, we can go to this cube here, and what we're going to do is, instead of using our test here, we are going to use our LdotN template. Let's see if it breaks. Of course it breaks. All right, now for this. Now notice that it is automatically calculating or updating the shader as we're changing it, which is kind of cool. Unfortunately, we're going to have to go here to figure out what exactly our problem is. Probably a nice typo. All right, let's see what it says. It says, we don't care about that. Diffuse undefined. So we haven't renamed our diffuse everywhere. This is what I get when I rename variables. So, oh, right in the code that we just created. We call that diffuse light. All right, now that should recompile. So no errors popped up. And we can see that our cube has actually got a lighter side and a darker side. It looks even like that one. Now, I just want to make sure that we are running the right code. Yes, we are. So just wanted to make sure that we're not accidentally doing something different. But no, we are having our thing. Now, one of the things that we can also see to sort of prove this is if we grab this cube and we move it over. Hey, okay, so no, we aren't using the right thing right now. Why are we not using the right thing right now? It's using the built-in shader. Okay, let's go and do that trick over here, actually, where we're going to say frag color.r is 1.0. Because remember, we didn't put any shadows in there. So that's not doing it this time. Why not? Okay, I'm going to just go and reload current project, because now I think that we are not getting the right thing. Okay, now it's getting strange. Why? Okay, this is also annoying that we are actually need to start it differently. But we'll do that in a minute. So why are we not getting the right version? That's interesting. So for this cube, we're using TestGD shader. Supposed to be doing that one. We're not getting any errors in here of it not being found, so that's not the problem. Unless I am not giving that error, that would be stupid. Why are you not working? Okay. Let me just restart this from here so that we actually get output. Maybe it doesn't like the fact that I've got capitals in that name. I don't know. Then again, when we had a bug in there, it nicely gave the error, which means that it was being used. Okay. Here we go. All right. Well, we can force that and see if we can make it fail. No, you can see that it's not getting in there. So why is it not recompiling our shader? Let's do this. That sometimes, yeah, now it comes in. All right. I'm not quite sure what's going on here, but I think our, oops, go on, just today, please. I think my problem is that it's not triggering the reload. There's still a problem in the reload logic. Although now it's not complaining again. Even though we still have this in there. Why is it doing that? I think my problem might be that it's caching it through this one. Okay, what I'm going to do is I am going to create a new, no, not a standard material, a new shader material. Now I'm going to go do this. Yeah, whatever color I want. That's all right. 3, 2, 1. Why is that not working? It should be good. 3, 2, 1 should be the. Oh, because I haven't assigned the texture yet. Ha 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 ha! So funny. There we go. Boom. Okay, and actually, I want to give this a different color just to set it apart, like that. But it is still not taking a template in. Is that because my test material is still cached? That could be the case. Again, I'm just going through sort of options that might explain why it is not dealing with my shader correctly. Output, what is that not doing? So here we are getting errors. Let me fix it again. Yeah, that's an old error. See, there's something still being cached. Because we already have that corrected. Okay. This is what you get testing on brand new stuff that hasn't gone through the proper test yet. Yep, let's rerun this. Oh, that was too quick. Let's see if I can beat it. Might have been in time. We'll see. I just deleted my shader cache, so that will force everything to recompile. And hopefully that will help. No, it's still... This makes no sense. Oh, I can't see. There we go. Come on. There we go. This is the downside of having a bigger screen. I need to size this properly so that it's actually correct for you guys. So why is this not working? Are we gonna do some debugging on that today? Well, the issue is that it's actually no longer using my template, and I'm wondering if that could be that it's getting confused. Oh, no, because it's not using the other templates. Okay. Let's see. If I'm going... Well, I guess we're going to be doing a bit of debugging tonight and see what we can figure out. Why it suddenly decided not to do what it's supposed to do. For that, we're going to go into... Not that. We're going to go into here. We're going to go into here. And we're going to put a breakpoint there. Let's start with that. Okay, that means that if I just give this a new line, it will go and recompile. So we have a template ID there. Okay. So there we go. We have a template. It's not initialized. Okay. That's interesting. I'm not going to go through all of that. Okay, hold on. Can we... Let's actually do this again. Oh. Why is it running through this twice? Template, initialize is true. Does it think that it has two? And why is it not initialized again? Okay. Both of these go right. Oh. Okay, sorry, it is initialized this time. Okay. All right, so it's... Why does it keep going through this? Why is it so many times assigning this? So yeah, that is... It has that one. How weird is that? I am guessing that because I'm typing, it must have gotten that multiple times. That's so weird. All right, I'm gonna just see what happens if I do that again. Because that is getting it out of our resource. So that is getting the cached version. Okay. Okay. Here's a fragment shader. Let's see if that is the fragment shader that we expect it to be. Copy value. Why doesn't it do the whole thing? That is supposed to work. Yeah, I'll check that in a second, but I did. Come on. Reference. Fragment shader code. Oh, I needed to get this one. So copy value. Well, that is definitely the right fragment code, so we definitely have the right template. Well, the other thing that I'm wondering about is maybe we're using the separate specular mode, because I might have some things on and I'm thinking that I'm using the wrong version, but I'm actually using the right version. Although we... Oh yeah, this... don't do that. That's weird bug. No, we're still casting shadows, and we don't have shadow logic on that, so I don't get it. Because the other thing that I was thinking about is that maybe I need to just do diffuse lights, but might need to just put that there. But I'm actually pretty sure that it's not running through my template logic. All right. That doesn't make any sense because we are compiling this one. We saw that it's loading the right template. So the only other option is that it's, I don't know, because as long as there's a template, then it should run through this. I'm off by one on the indexing. Okay. Yeah, let's just do a new file, test2, templates. No, it's not. Yeah, and I'm just going to put this here because if we're using the correct shader, we should not be seeing shadows, and we should see it that it colors red. It is getting that in there, but it makes no sense. Which I lost where we had the code before. It's a bit of a shame. Because also I'm not keeping a copy of whatever shader I was using. Although maybe that is in there. So let's just do this. Let's go and it's overkill, but just to trigger a rehash. Okay, that should now be using that. And that should now have triggered a reload, but it didn't. Okay, let's just go back to this one. That will definitely do this. Okay. Step into. We're over here. So now we get our shader templates. Actually, I want to have a look at our shader template there. Do we? We should have text versions in here. So here we go. So our fragment shader should be this, I think. Chunks. Oh yeah, because it breaks this up in chunks. I think this last one. Okay, cow data pointer. Copy value. I just want to oops, not there. Oh, I already closed that. That's not smart. I just want to verify that this is indeed the right one. So here we indeed have our diffuse light R. So it is the correct shader. So the only thing that I can think of, yeah, forward clustered. Oh, you could have even seen it here. The name is nicely forward clustered LdotN. That's exactly what it's supposed to be. So as far as I can see, we are using the right shader. Yet it's not combining it with that shader. And the only thing that I can think of is that it's caching it wrong. Which does not make any sense. So even if, let's see if we can do this. So if we go to material override, inspect native code, let's see if we can see that it's actually using our code or not. Because that's my main fear here, is that it's cached the wrong version at some point, and it just keeps picking that up. Because the caching isn't aware of the fact that we're using different templates. But then again, if we then change the code, it should always recompile, and it should therefore use the correct version. So very confusing. Let's assume that it's one of these again. Okay, so this should be the first one. And then look at the fragment shader. Is this our fragment shader? So that's all the injected code. That's all fine. We need to go all the way to the bottom. No, that is not the right code. What the heck? Okay, let's see if it does that for all the versions. No, that's our built-in shader. So that makes no sense. We are using the right shader here. Okay, I am lost for words. I think that I need to spend some more time on this. Like, I'm going to do one more thing, just to rule out a worry that I have. Well, let's go and have a look at, because this should now be using the built-in shader. Step over, step over, step over. There we go. No, that's still. That's interesting. I guess that's because we're on Windows and it's not case sensitive. Even though. I wonder if it's because I duplicated things. I wonder about that. Okay. So where's our second cube? Here's our second cube. Let's go and clear. Okay. Cool. Let's go and quit out of this. I'm gonna go here first. I'm gonna rename this to be LdotN. Again, I'm just ruling out the weird things. See if it has some problems with it being case sensitive or something. It shouldn't be. You never know. Now the other thing that I want to do. Come on. There we go. Test. Let's see. Let's see if this gives us any clue. Where are you? Test custom. So here's my projects. If you go into .Godot, we have a shader cache here. Lots and lots of shader caches. Somewhere in here, we here have our forward cluster LdotN. So that's the one that it's using. So let's go and take these two and say delete. Okay. All right. And then we go and rerun. Let's not do that. Okay. Okay. So, first things first. We still only have the forward cluster test in here. So that's what I was expecting. Because right now, even though our template exists here, we're not using it. We do have our shader here, but this test shader, you know what? I'm going to rename this to test. And we are going to create a new shader here. So I'm going to go copy this, paste that in here. LdotN, because that's the other option, right? That, oops, I don't want to save that. That maybe because we just reuse that shader, there's something behind the scenes that is still linking it to that one or something that confuses the heck out of it. So, new shader material, new shader, and we're going to call that LdotN shader. Boom. Creates. Right, there we go. And we're going to paste that guy in there. and immediately we get an error. Okay, that's kind of a good thing. Let's see, what's the error? Let's see if the error makes sense. Here we go. UV undeclared identifier on 750. Why would it say that? That doesn't make much sense. UV2 goes to, oh, okay, because I'm copying that there. Hey girls, how you going? But we're using UV both here and here. If UV used. But I guess we're not defining UV used. No, we're not defining UV used. So even though we're using UV. Well, we're trying to get my custom shader templates to work properly, but it's having some weird issues around caching mostly, or I think around caching. So let's go and actually say I'm actually going to complete our UV2 used. So here we go. So let's go and add this one in. Oh, we need to renumber 3, 4, 5, 6. Now we need to mirror that on the other side. That becomes in. Oh yeah, QB, you know, it's, what is it? It's past midnight already? Yeah, it's way past midnight already here. So if we don't figure this out in the next 15 minutes, this is going to be, let's end it here and sleep over it and then stream again tomorrow. And hopefully tomorrow we will have an answer. Okay, so now that can be over here. And now I can simply say UV2. UV2 interpolations. There we go. And with that, we remove the risk of that going wrong. Okay. So being black now can just be because of this. So we definitely have that working. But we might already be, no, we don't have shadow. So that looks promising. Load. Beta 3, 2, 1. Okay, and I actually do want that like that. Okay, 3, 2, 1. We don't have shadow, so that's promising. But what happened to our? We're making diffuse light R1. Because with that, we should be overpowering our diffuse. Oh, but we also don't have directional lights. Go back. That should all be. I actually don't care about these at all. They are not related to what we're doing. Oh. What? I thought we copied that. Oh, I guess we didn't. LdotN. Okay. And now we have our shadow back, which means that we're not running the right shader. Oh my god, this is frustrating. And it makes no sense. It's like it's not grabbing the right template. Even though when we step through it, we can see that it is grabbing the right template. But when we do it over here, even if we do this and we do this, it takes forever. Come on, open up. You go to Fragment. Well, we can already see that it's long. So that's definitely the wrong one. That's our built-in one. Okay, so if we go back to test, then we can see that that does change it. So now it's actually using the test one. And if we now do this, yeah, it's definitely still doing something weird. That's our code. So let's go again to version that and then to fragments. And we can see that's all old test code. So this one is using the right one and the other one isn't. So somehow this does not work properly. If I have more than one template, it's getting confused. It's using the wrong one at that point in time. Even though when we step through the code, we can see that it ends up using the same one. And it's not just that if it goes to LdotN that it switches back to you know, that it's switching back to the test template. It's using the built-in one, even though it's not accessing the built-in one. That makes no sense. So something is not working the way that it's supposed to in here. We can see that when it goes through this, it is grabbing the template that we are supposed to grab. Now we are using a single shader compiler here. Yeah, I can definitely try it out, seeing if it's getting confused between things. So if we do a 3D scene here, and let's just use our default lighting, mesh instance, 3D. Let's go through a box there. There's a box. Hello. Let's create a shader material. Boom. And we're going to go and let's just load our. There we go. Well, it should already be red at this point in time. Yep. Some color. There we go. Oh, because we didn't do LdotN. It's not red. But that could, of course, be because we had all these other things loaded. No, it's supposed to make a red cube because we are overriding the color. I don't get this. Okay. Close that one. I'm guessing that should all be out of memory now. So if I go back in here. Oh, let's put it over there. Okay. There's a shader cache for that one. Let's delete that one again. Just get this. No, that's still getting it out of memory. But that one. That's a template. So I just put that in to make sure that our red is always full. So we should always see the cube at least want some sort of red color. But it's just not using that one. That makes no sense because especially when we do this, oops, not that. We do this, and then that, we should be seeing the right shader code. We're not. Because for some reason it's going to the wrong shader. Yeah, I could do it on the frag color directly. But I just did it on the diffuse just in case that one define was set. But actually, let's double check that because we can see that in this. I suddenly realized that I can also force a breakpoint on this to see. Yeah, so we're not doing any other defines, so that's good. See, this is already the built-in one. However, before we do that trick, I just want to do one more thing here. I want to go to get native source code. I'm going to put a breakpoint here because as far as I know, that is what this calls. Okay, so we have a shader template. We have a version doing here. Okay, so step into. So let's first see if we now have the template that we're expecting to have. Shader. No, that's our scene for clustered shader RD. All right. So where are we coming from for this? Because this is... It's coming to that. This is the editor. Here we go. Spec shader, P shader. Get native source code. Okay. All right, so it has to be that it's somehow getting cleared. Hmm. Why does it do that? What am I missing here? Oh. Yeah, that's what I'm, yeah, exactly, QE. That's just that test one. So it's either a problem with the fact that I've got more than one template now, or I am just overlooking something really, really dumb. And I think what I want to do is let's see. Let's just include set code. All right. So, set code. Because there has to be something that's going wrong with this. Boom. Okay. So, and if I remember correctly, this is actually run twice. Apply shaders. Okay. Oh, that's actually coming from that. Okay, that's fine. Because now it's setting that without actually saving it, but that's good. So set path. Yep, that's good. Go preprocess. I'm happy about that. Okay. All right. And I know that we've already checked this, but I'm going to check it again. This is going through shader templates, fragment, shader, and that's indeed LdotN. Oh, come on, don't do that to me, please. Okay, that definitely should be good. Okay, so now let's go in here, step into, boom, step into, boom, step into. That's now return the rids, that's fine. Step into, So annoying getting through these things. Into almost. Into again. Yay, we're finally there. All right. So here goes false. It's interesting because I thought that should be true. I guess we're about to set that one. Oh, but in this case it doesn't matter because we're working on a new. I might want to put it in there. That's actually a fix that I need to do. Okay, so here's a shader template with a shader, which is indeed our forward cluster. So that's the right shader. Okay, cool. We can delete that. That's cool. Okay, that didn't have a shader template before. Now it has a shader template, and now we do that. And it's going to reapply the code. That's fine. Yeah, that's fine. That's the optimization that I still need to do because it's going to set the code again over here. Step into, and I get all this again. Yeah, that's fine. Step into. All right, let's see if it still has the right. Oh. Here we don't have it. What? Okay, we've lost our template here. But we just assigned that. We just assigned it. Okay, I think we found a possible culprit. But how? Why did that get unset? Okay. Move our breakpoint a bit down. Okay, we're on to something. All right. Now, I do want to put the true in there, but... All right. Step into. Step into. Step into. Step into. Step into. Ding, ding. Okay, love macros. There we go. Boom, we're in the right one. Okay, so we have a shader template here. Wait. If the shader template that we currently have, which is null, let's also see what this is. All right, LdotN shader, so it's pointing to the right one. 265. 265. Okay, let's remember 265. Okay, we're deleting our shader data. And if we have one, which we don't, let me assign it. Here we have one. That one's null. Okay. So now our shader template is set. So we have a shader template on 265. Data is null. That's what it's supposed to be. Okay. And we insert us as a owner. Cool. shader. 265 has a shader template. It's our LDOT. Okay, so let's see. At this point, oh yeah, because we undid the type. That's fine. That's indeed something that we need to do. Okay. That's good. Okay. That's still set. Come on. So now we have the correct grid here. Perfect. Okay, what I want to do, just in case that this somehow gets called again, just put a breakpoint there. Because something is undoing it. So here it's compiled with the correct one. All right. Oh. Oh. Where is that coming from? Shader template free. Why are we being freed? Okay, here's a shader template is being deleted. Oh, that's stupid. Oh, that's a change that I made really last minute. And the reason why that's not going wrong with the other one is because we have a material that actually keeps it. So our problem here is I'm not keeping my reference. So my reference here is temporary. Oh. Okay. We can fix that. We can fix that for sure. But oof. We have to keep our reference to our shader template. All right. Let's fix that bug, shall we? So I actually need to make sure that we keep that. And originally that was a property. And then I went like, I don't need that property anymore. But with that, I completely screwed this up. So we're going to go over here first. We can move you in here. Oh no, I'm actually going to keep that here. Because here I can't include it because I also get it, or what you call those things when two dependencies work two ways. So I'm just going to class define that here. And then here we're going to have mode and we're going to have ref shader templates. Shader templates. There we go. And then over here in our get code, we're going to go and do here is ref shader template, new templates. Boom. Okay. Then what we're going to do is let's move you here for a minute. We're going to deal with that in a minute. Instead here, we're going to say if our shader path is not empty, bye-bye. Then new template is going to become our that. Now we can say here if our shader template is not equal. No, I actually want to write that out full. That's nicer. Yeah. So if we've changed whether it's unset or not, we can now say if it is valid, we set that, and we're also now going to send here true because we don't care about keeping the code. And if not, we're going to set false, which also means that if our shader template doesn't change, we don't have to update that on our template. Because as far as I'm aware, this is the only place that we're doing this. Perfect. So I think with that, we should hopefully have fixed our problem. Whoa, that was a crazy one. And of course, our class has changed, so it needs to recompile almost everything. There are some weird dependencies in our system. So this will take a minute before we know if this was indeed the problem. But I do think that this is indeed where things went wrong. Yeah, that'll be fine at the end of the day. That's always the one, isn't it? And in this case, it was like, oh yeah, I added that when that still needed to be a property. Oh, it's no longer a property. I can just remove that. Oh yeah, no, I'm still using it here. I can simplify that code. Yeah. Famous last words. Absolutely famous last words. But we're getting close. We're getting real close. Oh, boy. I'm tired too. Wonder why. Oh yeah, because it's 1 o'clock. And I still have a XR meeting to do tomorrow morning, so that's going to be fun. I'm going to wake up in time for that one. Do I get myself into these problems? Okay. Let's not go through that breakpoint. Let's go and... still not looking the way that I'm hoping that it would look. Okay. So let's see if this code actually does what it's supposed to do. I bet you we've still done something wrong. So we have an empty reference. Perfect. We have a path. Load LdotN. Okay. Resource loader. There is our resource. Gonna assume that's good. All right. New template is that. Current template is nothing. All right. New template. Oh, yep. Let's just stop this already, because it might be very smart to actually say assign it, because we still haven't fixed our bug. And then we're going to actually use the template as is. There we go. Because without that, we are still releasing our template. Because we have to keep it somewhere. We have to keep a reference, else we're still destroying it. Okay. I want to get rid of that breakpoint again, because we're going to run through too many of those. Get rid of you as well for now. It's red. It's actually red. Don't do full screen. I wish you could specify sizes of that inbuilt logic in Windows 10 for screen positioning. That is red. Okay, cool. Bye-bye test scene. Back to main scene. Here's our red one. Cool. I'm surprised that our diffuse logic works the way that it does. Okay, we're definitely doing something wrong with our LdotN logic, but let's first, yeah, it lives. Let's first go back in here and remove our funky red thing. Okay, so we can definitely see. Okay, what I actually want to do first is, oh, we can actually just take that out. Let's see if our ambient light does anything that makes sense. Okay. And that's logical, because I actually don't have ambient light on. So my ambient light is completely dark. And that is because in our world environment, we're getting our ambient light fully from a sky contribution. So if I want to have that, I need to lower this a little bit and make sure that I have a little bit of light there. And actually the sky contribution doesn't matter, because I'm not even using sky contribution. I'm just using the color regardless of my source. I'm ignoring the source here. So that is actually directly influencing my things. That's, yeah, that's what you get when you don't implement all the settings. So that bit works. Now, if we add our diffuse light back in, we can see that our diffuse light is not working the way that it should. Totally not. That is not doing anything that it should. Now, let's go back here and see what we're doing with our normal. So as far as I'm aware, actually, that's a good point. What are we doing with our normal in our vertex shader? So let's look at our vertex shader. We can see that our normal entropy is calculated using our model view. So that should indeed be yep. So yeah, majors are always a pain in the butt, aren't they? Okay, so it could be that we are normal map. So that's if we do a normal map. We don't. So our normal is coming back in the way that it is. So we do have normal used here. So that is just, yeah, that's just what it is. I don't think we have anything to do with that, so that's good. Oh yeah, no, it's always a pain in the butt. All right, so we know that our ambient light works correct. That's cool. So here we're going through our directional light. And we're getting our color, we're getting our energy, and we're getting our direction. Okay, hold on. We have light, no, that's light direction. Yeah. And we are multiplying that with our view matrix because our direction is in world space. I think is our direction in world space. Let's start there. Maybe it's not, but I do think it is. Or maybe it's already in. It's a good question. Maybe direction is already in view space. Let's see how that is in here. Okay. I have a feeling light direction. Okay, I have a feeling that our direction is already in view space. So we actually don't need to do that. Okay, let's see. That didn't compile right away. Am I in the... Okay, so now at least it's stable. And it looks correct. So if we go to our directional lights, let's go and move that down a bit so that we can actually play with that easily. And we go and do that. Yeah, that kind of looks the way that I expect it to. Okay, so one thing that I have a problem with and why it goes all black is because this can go negative as well when it goes beyond 90 degrees. And we actually don't want that. So I guess let's actually do that with a clamp. And we're going to restrict that between 0 and 1. Okay, now we get our ambient light still in there. So, oops. Instead of it going completely black, okay. So we have our directional light working right now. Let's for fun. Actually, let's start with an omni lights. Let's go and put you up. And then to differentiate that one, we want that to be a nice red sort of light, a pink. Pink is cool. I like pink. So I'm going to turn that up a bit so that we can really see like, hey, that is actually coloring that, but it's not doing anything with that. And it's definitely not doing anything with that. Now I am going to leave it there tonight because I am way past my bedtime. But next stream we can start looking at actually implementing omni lights in this as well. And again, I'm going to do exactly the same thing as we're doing with our directional light, is just do it with a normal LdotN calculation and then purely do a range restriction. So making sure that we only apply the light within range and that we have a fall off by attenuation. And then slowly make sure that we support all different light types. Now again, I haven't done shadows yet. So it casts shadows, but it doesn't receive shadows, which is fine. But yeah, for the most part, it works. So yeah, I hope everybody enjoyed that. I'm going to definitely leave this video up. This is also a weird problem that sometimes, all of a sudden, even though I don't have snap turned on, it suddenly decides to snap. And the snap reverses. I wonder what sort of weird bug that is. Anyway, so yeah, we fixed an important bug. That's pretty cool. We now have an example here of how you loop through the directional lights. Now the omni lights and spotlights is similar in the way that it loops through that, but the calculation that we have for those is different. And yeah, normally you would have something like this that would be repeated in the light calculation here. Shortcuts, maybe, yeah. This is all shortcuts, obviously, because the whole point here is to create a template for a much simpler shading logic. Oh yeah, what's your request, QB? You can get syntax highlights. You mean in here? Isn't there like a plugin? Oh, yeah, but this is not recognized as a GLSL type file. I need to look into that because I'm pretty sure that there's a GLSL extension in here. So we can actually have a quick Google for that or search for that. Yeah, so it definitely has a GLSL shading language thing. It actually has a couple of things like that. Is this free? That's a preview version, so that might not even be free, but well, it comes 5-star. But the question is, can I then configure this to do additional syntax code snippets, syntax for Minecraft shader packs? I just want to, let's go and install that. And extensions, so no. I want to know if I can add additional extensions in here. Okay. Oh yeah, maybe the snapping thing was shortcuts. That's possible. Accidentally hit something. VS Code app extensions to language. There we go. How to associate. All right. Okay, file associated, but that is the old settings. What's the new one then? Here we go. The easiest way I found is to simply Ctrl K M or Ctrl Shift P. Okay. Oops. Sorry. Ctrl K M. That doesn't work. Okay, Ctrl Shift P. Here we go. No, configure. Oh, file associations. Okay. Control Shift P. File. So. Oh, I don't have that option. So maybe I need to do the old way or something. I don't know. How would that be done? Help. Oh, hold on. One of the things that I might be able to do. Plain text. Here we go. Configure file associations for that. Here we go. GLSL. Boom. Cool. Colors. I probably should be able to do the same with GD Shader. Say instead of plain text, GLSL. Bonk. Oh, there we go. Not sure how useful these colors are, but we have colors. Now, I wonder how well the autocompletion with this works. I do get that autocompletion with that. That's pretty cool. All right. So yeah, QB, there you go. You just need to install a GLSL extension, and then in the right bottom corner, you can link your. And I don't know if that extension that I installed is the best one, because there's a whole bunch of them. But yeah, it does that, and it does some amount of autocompletion, so that's pretty decent, I think. Pretty cool. Ah, learned something new. Very cool. All right. All right, everybody. That's enough for me, I think. I am pretty tired now. But I think that was really, really useful. And we, like I said, we fixed a bug. We got basic lighting working in our template. And our example is getting nicer and nicer, so I'm pretty happy about that. I think I'm going to delete this test scene. We don't need that one anymore. Here, delete. Boom. All right, I will put links on the description of this stream to everything that is relevant here, and yeah, we'll keep it there. And I bid everybody a good night. Yeah, cool. Thanks everybody for watching, and I hope you guys enjoyed it. See you next time.